All right, 5 o'clock. Hi, everyone. I see Yash over there on the left-hand side for me. Daniel Bai, Kayan Yu, Shuai Liu. Okay, 107 participants from Yash Gupta to everyone. Hello, everyone. Hi, Yash.
Hello, Professor.
Hi there. Cool. Can you hear me? Okay, so share screen and start. Someone is speaking. I'm not sure if that was meant for me, but I couldn't hear you. Your audio was cutting out. Sorry. I hope my audio is not cutting out. Okay, wait. Chat. I gotta put the chat up on this side. Okay, so people said, hi guys. Yeah, you can start whenever you're ready. Okay, thank you. All right, so I'm gonna switch back to everyone. Good. So as you know, your homework is not there yet because your first homework is an entity relationship diagram homework. So you are supposed to read a bunch of words which describe how, you know, something works, like how we loosely call everything a business, but how something works, like how an airport works, or even how USC works, and then come up with these things called entities, which really are tables of data, multiple tables of data, and then find a way to connect them, link them. All the connection is where the magic is. Why does this table relate to that table? So that is called a relationship. So you need to submit as your result entity relationship diagram. This is a very common operation in engineering. We're modeling. So we're modeling the real world after removing all the abstractions and simplifying it, but still putting enough information inside for it to be useful. Because this data, the entity relationship diagram will actually turn into a real database, and then people will start adding data, and you can get your USC transcripts, you can get your course catalog, you can see what your dining bill was for the last month, you can borrow library books, you can play sports. So these are real things that happen in the world, and then they're all tables of data. This is very interesting. So in the first class last week, I was asking you what is information, and then how do you turn that into knowledge, you process it, meaning you learn something from the information. You can keep going and you can call it experience. If you do it enough number of times, the knowledge becomes automatic. You can see a situation, instantly know what to do. Experienced CEOs, CTOs, people in the world, that's experience. This is just for fun. So then you can have what's called overfitting. You can learn too much about your data, and then you can draw all these fancy pictures. Couldn't find your name. I'm looking here. Oh my goodness. All right. Oh, oh, oh. Wait, I gotta type something important. Wait, would you? We have
Oh,
a
I'm
question.
here.
Okay. Yeah. So yeah, go ahead, Jim.
Perfect. Hey, sorry to interrupt. Thank you so much. Hey everybody. My name is Jim Huntley. I'm a professor in USC Games. Sorry, it's such a huge class. I couldn't find out how to DM your professor really quickly. But he was gracious enough to give me 5 minutes, no more, for some quick announcements. Our program is jointly shared between the School of Cinematic Arts and the Viterbi School of Engineering. I'll show you a quick presentation. I'll also put the presentation into the chat when we're done, so you can look at all the links and how to contact people and stuff. So, but if you have any questions, all of my contact information is at the very end of this presentation as well. So let me share my screen. I will jam through this and be out of your hair so you can get back to your lecture. Can everyone see the PowerPoint on my screen by any chance or no?
Yes.
Okay, awesome. All right, I won't put presentation mode because that obviously hides a bunch of stuff. But a couple of things. AGP, the Advanced Games Projects class, the capstone class for USD Games are one of them. This year's game lineup will be revealed in this year's Expo on May 13th. If you're looking to crew on a game as a volunteer for spring, even if you didn't attend AGP in the fall, that's okay. Just go to our crew event. It's going to be happening this Thursday after class at 5:30. Is that tomorrow? That is tomorrow. Tomorrow at 5:30 after our main AGP class. Feel free to listen to presentations of the crews or teams that are still looking for crew. And if there's a game that you find interesting, certainly raise your hand. We'll have a form there where you can sign up. That's AGP 2021. AGP 2022, which I'm horrified every time I say because it sounds like it's in the far, far future that requires a time machine. But AGP 2022 We're going to have the first orientation meeting about that on February 4th at 5:30. If you want to be, make sure that you get invited to that. Please also email me directly, and I'll make sure when the invite information goes out that you are on that list. We'll be promoting it on social media, et cetera, too. But I want to make sure anyone who is interested knows that it's coming up. Our expo for this year is going to be May 13th. We'll be streaming it again on our Twitch channel, USC Games. We have games that are made inside of class, outside of class, members of the program, any Trojans around USC, and alumni. So if you've been working on a game with some friends on the side or yourself, and you're like, hey, I'd love to get this national platform at my school to showcase what I've worked on, please go to uscgamesexpo.com, submit the information. We'll review the content and get back to you within around 30 days of submission and let you know whether or not you'll be featured in the May showcase or not. Last couple of things also related to Expo. If you're looking to help out with the stream itself, you want to get into streaming and learn how to do a professional stream, reach out through our USC Games email address. Tell them that you want to be an Expo volunteer for 2021. We are open for business and looking for people to sign up. Last couple of things, campus gaming. And like I said, I'm flying, so I'll have the contact information for this stuff later. Campus gaming, we're going to start doing more casual games across campus just as a social thing. Well, we wanted to do more of that during the pandemic. We're definitely going to start this spring with some of that stuff, whether it's school versus school or res hall versus res hall. We want to do more Mario Kart Among Us, like casual games that people can have fun playing, but we can also stream and drive awareness behind the gaming community on campus as well. The big doggy, second from the last thing, is streaming production. If you all pay attention to esports at all, we actually started an organization called the PAC-U this past fall. We basically had USC and 10 other PAC-U schools, 11 of the 12, all competing with League of Legends, Overwatch, and Rocket League. We'll have 3 new games this spring. We'll also have a lot of opportunity to learn how to stream. So we're getting some pro streamers and pro esports organizations to come in and give us guest lectures. If you want to learn how to be a technical director, a producer, observer of a game, and many, many other roles, click on the link and fill that form out there. And we'd be glad to have you and glad to have you trained up in the boot camps we'll be having throughout the month of February. And then last but not least, League of Legends varsity tryouts. We had one round for spring already when we first got back. We're going to have another one in April. If you want to check out the form and look at the requirements, but if you are a hardcore league player and you want to, suit up in the jersey, I guess in the privacy of your own home where no one can see it, or suit up in the jersey when we get back on in a physical location on campus, this is the time to try out. And last but not least, that's my contact information. That's also my time, 5 minutes solid. Thanks a lot, Professor. If anyone has any questions, feel free to hit me up. Otherwise, I'll upload this presentation in the chat and you all can follow up on whichever initiatives you find interesting. Thanks so much.
Wow, very nice, Professor Huntley. Thank you so much.
Thank you.
Right on time. Cool. Okay. So Jim is going to put up the link if you guys want to click on it afterwards. This is very good stuff, by the way. So it's a USC, games program. So this is your chance to, be involved if you want. Okay, I'm going to go back to sharing my screen again. Share. Cool. And then the chat went away. Put the chat back. Yeah, there it is. Okay, so it's in the chat. Maybe what I should do is actually download it and then possibly, just put it up once again in our course page. Okay, so let me do that afterwards. Okay, cool. Good. So that's happening. Very good. Yeah. So here, what I was saying was, this is for fun, but actually in machine learning, this is something that does tend to happen. When someone gives you a lot of data and then you analyze the data, what you want in general is to learn the pattern, the overall pattern that might be in the data. Don't do something called overlearning. So overlearning is come up with new patterns that really are not there in every piece of data, meaning this one happens to look like a cat, but the next one might not. That is called overfitting. So it is funny, but it's also in a way not funny. So I tend to put up things like these for you. Let's not click on extras, grading, nothing has changed. So I want to talk about ER diagrams, like I said, right? For the next hour, we'll talk about ER diagrams. That starts here and actually continues here. So this is what we're going to do till about roughly 6:15, okay? In other words, I'm going back. That's fun at a time, okay? So you can mail Jim to find out. That's funny. No talk about data right now. Dota, sorry. So look, data, not Dota. So I'm going to go backwards. With these arrow keys, you can also find out something cool. Unlike classic PowerPoint and PDF, it's like a doubly linked circular list. And so you can, like a slide carousel, I can go backwards and forwards. So we're here last time, just starting to talk about this notion of relational model. So in a relational model, ultimately, so we'll draw more diagrams, but I think I talked about this. Data in general does not have to look like a hierarchy, doesn't have to look like a network. Data looks like tables. Everything looks like a table of something, a table of books that Amazon sells, a table of courses you're taking this term, a table of students in my class, a table of all the restaurants that are near campus, a table of all the books that a library owns, a table of all the stocks that you own. Table, table, table. Everything is table. So in a table, a row is like one object. A row can be one stock, one book, one piece of food that you ate, one course that you did last term. Columns are all the characteristics. Columns are what describe the data. So say one row is a student in my class in CS585. What does it mean to be a student? A student has a first name, last name, their student ID, they have a major, they have an advisor's name, they have a graduation date, they have a column that says whether they're undergrad, master's, PhD. There's a GPA column. There's like all kinds, right? Your school, your department. Those are all called columns. So that is what these are. And then rows are for one student, for one, like I said, one library book, one piece of clothing that you own. Therefore, that is the most common way to describe any piece of data in the world, even with NoSQL, that didn't change, okay? So tables are tables are tables. But now we can start to connect tables together. Okay. So that's what this actually says, structural independence using independent tables. You never think of one giant table and then just say for all of the USC, everything that USC ever does, will stuff all the data in one table. That's very silly. There's too much of not separation of concerns. In programming, we have this idea called separation of concerns. What it means is a class definition for something should only be about the thing. It should not be about everything in the world. That's why you write many classes and objects can send messages to each other. Likewise, you define many tables and then interact between them. So tables are very simple because if I took one row, say this blue is one student, and there's a whole table full of other students, I can cut that whole student and paste them at the bottom of the whole table. Nothing changes because the student is still the same student. If the last column was a GPA column, I cut the entire GPA column for all the students and I paste it right here on the left-hand side. Nothing changes because it's still all relatively the same information. That is called conceptual simplicity. When you look at a table, it makes so much sense. Wow, I see exactly what they're doing. And then SQL that you will learn, soon. It's all about the SQL engine, the query that you write, going through every single row and saying, is it true? Is it true? Is it true? You're writing like if statements in SQL. So it analyzes rows of data. And the user does not have to worry about exactly how in the file format level data is stored. We started this class by saying file formats, the file way of storing data, not databases, is bad because you become dependent on how the file stores data. But now this is not our concern. It is the software driver's concern, such as Oracle driver. It can give you the data that you want. So I'll leave the chat on the side, okay? Well, press A, okay? A is the all key, okay? Press A and then just print it. You will get all the slides. A. Yeah, but do A first, exactly. All right. And then, so you don't need to worry about how the actual tables are all stored. And then it's just very simple to implement, meaning we at the higher level just write SQL commands to create the tables, SQL commands to add data, SQL commands to modify data, SQL commands to query the data. We never have to worry ever about how it is stored. So from now on, it's all about relations, okay, for the first half of the course. Forget like network hierarchy, because we can simulate all of them as if they're relations. So tables are pretty common. Okay, so the DBMS is just simply a collection of processes that manage this whole table stuff. I think I told you this. It's just some, ultimately some processes that stand between you. Conceptual simplicity just means easy to understand. It's almost like a class definition. When I show you a class hierarchy of some image processing software like Photoshop, you can just spend like a half an hour looking at all the classes. There's a convolution class, there's a file output class, there's a level class, there's a history class, there's a brush class. You see how all the classes fit together, and you say, wow, I understand the entire architecture. Likewise, an ER diagram, if you spend a few minutes on it, you will understand how the whole tables are all put together. That idea of being able to understand easily is called conceptual simplicity. All right, so now I'm going to tell you about relation. The fact that tables are related, that's what this is all about, okay? This said one to many, by the way, that just is a one to many. So that means this one table has many connections with this table. And I can start to maybe draw a few diagrams at this point. In other words, when you look at any two tables, we just consider two tables at a time. And then we ask how many different ways can you connect them? And we knew the answer from, last class. We can only connect two tables in exactly three different ways. For instance, say this is one table, and then there's another table. So then one row, like say, somebody here, can appear how many times in this other table. That is all connection means. So suppose there's some student here, and if the same student can appear here many times, that is called one to many, one to many. On the other hand, if something here can appear only one time here, it's one to one. And then if there's one to many this way, conversely, something here can appear many times in here, then it's one to many backwards as well. Then we call that situation many to many. So there's only three total, okay? All right, so then that is what our example right now is. Our example says, if I have a bunch of sales agents in a car dealership, these are all column names, okay? So a car dealership hires a car sales agent, a car salesman, saleswoman. You need to know their ID. Everybody has an ID, and then their last name, first name, like where they live, when they were hired by the car dealership, how much money they get paid, what's their salary, and then who is their employee, who's their manager. All kinds of things are stored about one single salesperson in one row of data, okay? So this is salesperson data. Just one row stores all the information about the salesperson. First name, last name, ID column, salary, manager, how good are they on a scale of 1 to 5? You can just put like a little rating there. On the other hand, imagine there's also customers. So this one is now customers, all the people that come in the car dealership and have bought cars over the past like 20 years. It's like a lot of people. No, there's no better way because the information is partly stored here and here. So you just have to make it as efficiently as you can, but there's no other way, okay? Yeah. Okay, so supposing one salesperson sold a car to this customer, and then after a few months sold it to this customer and sold it to this customer. The following will happen. In the customer table, there's a customer ID. In the salesperson table, there's a salesperson ID. In the customer table, the customer ID would be 1, 2, 3, 4 for every customer. But somewhere there's going to be a column called salesperson ID. And we make a very, very, very important conceptual assumption, which is if this salesperson ID was 5, and it says 5 here, then this salesperson sold that customer that car because that 5 is exactly the same as this 5. They're like one long piece of data, so to speak. If this 5 salesperson also sold the car to this customer and to this customer and to this customer, then if you look through this table and see how many 5s you can find, that means salesperson number 5 sold 4 cars overall. All right, so that's a very important, that is what's called a relation. So this wire that you draw means some column here, can be more than one column, but usually only one column, will appear in the other table also. That is all that wire means. Like I said, sometimes a wire might mean 2 columns here, might appear, both of them might appear here. So the number of columns appearing doesn't matter, but at least one column here is going to be repeated there. And that is a way to connect the 2 tables. So please understand that very simple, important things that I told you. Maybe we can just store the idea of 1, idea of 2. Yeah, sure. Yeah, definitely. There are all kinds of different ways to do it. Correct. So what he's saying is, you can make a third table. You can just make a third table. The third table only has 2 columns. One column says, salesperson ID, and then the other one has customer ID. And then you can have as many entries as you want. You can have salesperson ID 5, customer ID 1, salesperson ID 5, customer ID 10, salesperson ID 5, customer ID 100, salesperson ID 25, customer ID 3, and so on. Yeah, that's possible. When you implement, you do many different things, for many different reasons. So we're going to talk about all of that, okay? But right now, we'll just say this all it is. So that the notion of wiring is very important. Again, here the column names are vertical. In reality, in a table, the column names are horizontal. So for the customer, the main idea was this. Okay, now I'll tell you something so important, and then we'll keep repeating this many, many, many times. In fact, even NoSQL has exactly the same idea. In the agent table that I just drew and erased, an agent with an ID of 5 will appear exactly only one time. There's only one agent ever in that car dealership who has an ID of 5. Just like a student at USC or 10-digit ID does not belong to any other student because we use that one ID to look everything about you up. If we give the same 10-digit ID to 2 students, it's going to be mass confusion. One student is a medical doctor, the other student is like, a civil engineer, and then your transcript will get completely messed up. So of all the columns, things can repeat. 2 different agents can have the same city. They can be hired on the same date. They get the same salary. But that number must be unique in every single row. because that one column, that one value is what distinguishes every row from every other row. If that ID also becomes the same, then 2 rows or even 100 rows can be 100% identical, and we have no idea what the hell is going on. So we never allow that, okay? That column is super important. That column is called the primary key. Key means key. It is key to unlocking all this information. That's the primary key. Likewise, in the customer code, every new customer in that sales, in the car dealership gets a customer ID, like Amazon, gives you an ID. And the customer ID is what they use to look everything up. Your Ralph's Club card is like a customer ID for Ralph's. Again, that cannot be shared. No two people would ever have the same. On the other hand, in this table, in the customer table, this agent code, this same agent ID can repeat many times because it is not the primary key, okay? This is the primary key. Please understand. Yeah, sure, if you want. Yeah, you can make any row to be unique if you like, okay? But in general, primary keys are what we like to make unique. You're right, there's no connection between them. Okay, so this 5, the number 5, can be in 100. It means that person is very good. They sold 100 cars. If some other agent ID 10 is only in the customer database only one time in 10 years, that's probably not a very good salesperson. Nobody buys cars from them, okay? Probably need to fire them. Okay, so then when that primary ID goes in a new table where it's not the primary ID, we call it foreign key. Primary key becomes foreign key. Primary key, foreign key, primary key, foreign key. Please, please, please know that. That is all this relationship is about. Okay, I told you something very, very important. All right. So relational modeling involves relating one table to another table. Confusingly, a single table is also called a relation. So we use the word relation in 2 different ways, okay, in databases. On the one hand, the word relation means just one table is also called a relation. Like a whole table full of data, we call it a relation. And so why the hell do you call it a relation? Because every little piece of data, every cell is relating one row to one column. This cell is relating this row to that column. In that sense, even one table is called a relation, but we don't commonly use that. We don't make that usage. On the other hand, what we normally call a relation is when a table is connected to another table using primary keys, foreign keys. That is why we call it a relation. So this is an entity relation. That's why we call the whole diagram entity relationship diagram. Okay, so foreign key is this. In the salesperson table, imagine the salesperson's ID was called S, okay, like your student ID. In the customer table, the ID is called, the column is called C, so everybody has a different C. But this S can also be here as well. And at that point, this is now called a foreign key. Because again, if a salesperson has ID 100, then they sold to this customer, they also sold to this customer, and they also sold to this customer. So in this, there's no requirement that the value appear only one time, okay? Because it is not a primary key. It's called a foreign key, do you understand? Okay, one table is a relation because every piece of data in the table is supposed to relate that unique row because of the primary key and that unique column. Like, the whole table is a relation because that 3.9 is a relationship between your student ID and the GPA column. Computer science is a relationship between this student and the major column. Graduation date, some date is a relationship between that student and the graduation date column. So it's a weird usage, okay? It's not a common usage, what P is asking, but that is why a table is called a relation. Don't be confused. This is the bigger meaning of the word relation. I now want to move on, okay? But what I said was very important to you. Okay, so in the end, it's all about SQL. So SQL is what lets you create these entities. SQL also lets you connect them using primary keys and foreign keys. Then why don't we say a row column is a relation? Why a table is a relation? Well, yeah, we're all saying the same thing, This actually a row column is a relation. Like every cell, you agree that every cell, meaning every little piece of data, a cell can only have one piece of data, like an Excel spreadsheet. So we call that piece of data a relation. A relation is why the data exists in the first place. Whatever is there is connecting that column to that row. Yes, yeah. So every cell is a relation, correct. And more confusingly, the whole table is also called a relation. Okay, the word relation is extreme. It's a relationship relation, yes. So that is the bigger use for that word. A relationship is really why we should be calling this entire thing an ER diagram, because E just means that, and the other E also means that. So when you wire E's together using R's, we call them ER diagram. So what Matthew is asking is more the real meaning of the word relation. But what you guys are asking is all still relations, okay? See, please don't spend too much time on it. Don't be confused, okay? It just, like, if you ask me why, again, I told you, every column happens to be related to every row, meaning there's a value there, and which is called the value relation. All right, we should actually move on. So a collection of tables. In the end, your so-called database is ultimately a collection of tables. Again, tables are entities. And tables are all separate. One table really has nothing to do with each other, except when you connect them. So when you make a relationship, then they become connected. So this is what I just told you. So rows in different tables, such as, a student and a course. So a student can point to many courses, and that's a relationship because the student is taking all those courses. And so then there's a common value, meaning the student ID would also appear in some other table. So SQL is what ultimately makes all this possible. If you give me a little time when I get to our actual lecture, I will illustrate all this for you, I promise. I don't want to be like so behind and we'll never finish. Okay, sorry about that. All right, so an ER diagram or an ERD is ER diagram, or an ERM, ER model. They mean exactly the same thing. The diagram is the model is the diagram. In engineering, this is what happens. I model some chemical process system, then I call that the model. I call that the diagram. So diagram, model, they mean the same thing. And then every row, okay, now every single row is called entity instance. Okay, so now for more terminology. If the whole table is called entity, I told you can think of them as being made up of objects. First object, second object, third object, fourth object. Like, in programming, each is like an object because an object has many members and members are values. So therefore, objects are also called instances, right? If a table is called a class, then an object is called an instance. Likewise, if the whole entity is the class, then each row is called an entity instance. That's all it is. So entity instance is another name for a row of data. That's all. Entity instance. Okay, that's what this says. They're just rows. Okay, connectivity is the wires you draw between them. And there's only three kinds: one-to-one, one-to-many, many-to-many. So we said this a lot of times. I can skip it. Therefore, again, the same thing. So what is nice about drawing a diagram? Anybody in the world can just look at it. As long as you named all those with good nouns and good verbs, even a high school kid might know, wow, this is how DreamWorks works. They make movies, they show them in theaters, they have employees, they have, all that. Disadvantage. So then there is advantage. It's simple. And then it's also a communication tool. You can show the database diagram to anybody and they all understand where different pieces of data go. I don't even know what this means, So this means I can turn the diagram into an actual bunch of tables. I think I told you about UML the last time. So if you draw the diagram using UML, a lot of times there's a button you can click on, and the clicking will generate some SQL, and then you can run the SQL. You will get empty tables. An empty table has no row at all, but it has all the column names properly defined. And then I can insert first row, insert second row, insert third row. As DreamWorks makes movie number 1, movie number 2, you can start to populate the empty table. You can do that. What are the drawbacks? Oh, come on. Okay, I'm going to say, forget this. Just forget it. Okay, this is all not true. This is like BS. Okay, fake news. There's no disadvantages. I'm not joking. I'm actually serious. Okay, how do you actually draw those relations? Okay, suppose you have one painter such as Monet, or Van Gogh. This is a painter table. Every painter has their own line. Renoir has a line. Escher has a line. Joan Miro has a line. All these painters. A painter usually in their lifetime paints many, many, many paintings. So Renoir probably painted 100 Impressionist paintings. So there's a table with every single painting that all the painters painted. In the painter table, every painter has an ID, like student ID, 1, 2, 3, 4. In the painting table, every painting has an ID. But somewhere in the painting table is also a painter ID. So painter number 5, such as, again, Magritte. This guy painted all kinds of really cool surreal art. Magritte. So Magritte has an ID of 50. If Magritte painted 100 paintings, that'll be 100 times 50, 50, 50. So 1 to many. Commonly, a painting is painted only by one painter. Two different painters don't walk up to a painting and change it, right? That's weird. So it's 1 to many. It is not many to many. Okay. So something called the Chen notation. Chen actually was from UCLA. This was discovered right here in LA. He came up with a diamond to say, this is how you say the relationship. So draw the two entities, put the names, say 1M, 1 to many, and then put the verb that says paints. That's his notation. For many to many, he called it MN. An employee can learn many skills. They can learn C++, they can learn tax filing, they can learn 3D printing. So if I have a list of all the skills that an employee can have in a company, one employee's ID can occur many times. You also have skill IDs that is unique. but the employee ID can occur many times. So an employee can learn many skills. Likewise, a skill such as programming in C++ can be learned by many employees. So therefore, in the skill table, the employee ID can occur many times. In the employee table, the skill ID can occur many times. It's both, right? The columns can appear more than one time. So it's called many to many. And then finally, there's a one-to-one. Suppose you have all the employees that work at Starbucks in Los Angeles, and you have all the stores that are in Los Angeles. Then every store only has one manager. And if somebody is a manager, they manage only one store. So then Chen put a 1 and a 1. We don't use Chen's notation too much. This is UML, and then I'll finally tell you this. UML is the most modern notation. Sorry, it's a little hard to read, but I can show it to you. It just says things like 1, 1, 1, infinity, okay? So this is 1, 1, this is 1, star. Star is asterisk for multiple, right, from Unix. So that's the notation that they would use. So 1 and star, 1 and 1, 1 and 1 here, and then 1 and star, 1, 1, 1 star. This says 1, 1, 1 star. This says 1 star, 1 star. This says 1, 1, 1, 1. If you ask me, why do you think the 1 repeats? Here you only say it one time, here you said more times. Please wait, I'll explain it to you, okay? So right now I want to explain it to you. There's something called cardinality, and that's what they're talking about, and connectivity. So we're not there yet, so I'll not tell you why it is there 2 times, 2 times, 2 times, 2 times. Imagine it's there only 1 time. We don't use this in the world. This is the most common notation we use in the world. It's called crow's foot notation. So why crow's foot? Because you can have a little crow there. So you can have a little crow, a little crow, a little crow. Hey, crow's feet, look at it. Whee, cool, go crow. Crow. So then that is the crow's feet. Okay, so like that, that's the crow's feet. Now and therefore in crow's feet notation, it's pretty neat. 1-to-1 is just really one. Sorry, let's do 1 to many first. Again, 1 to many. Don't ask me about the extra vertical line. It is related to this extra occurrence. Right now, only think 1 line, many lines. Many to many is crow's feet here and also crow's feet here. Many to many. 1 line, 1 to 1. Okay, we'll get to why it's duplicated. Okay, I promise. Right now, 1 to many to many, 1 to 1. Okay, so please use crow's notation for your homework. In the world, that's what we use. If you wonder about notations and you say, wow, what else is there? There's one more called RAIN85. There's one more called IDFX. So this is there just to give you some extra info about notations. I won't ask any of this in the exam, just for fun. Because notations are fun, right? Because if you do a good job, see, RAIN is like more weird. It uses half diamonds, but the world just ignored it. We don't want too many different notations. So again, this is Amazon, right? Amazon Prime. A customer, every time they go and order something in the shopping cart, that's called an invoice, like all the things that you ordered that day or that time when you logged in. So a customer can obviously generate many invoices, okay? Like throughout the last 20 years, I probably bought like 100 different times from Amazon or more. Then each is called an invoice, a customer, many invoices. If you look in any one invoice, you don't order just one thing, you order maybe 5 things. So one invoice can contain many individual items. Each item that you order is called a line item because 1 line. And some human would actually go pick that up and drop it in a box and send it to you, right? Okay, so then this is very interesting. The line item and the product. So Amazon has a product catalog. They sell a million different things, right? So each product, can appear multiple times, right? So I can order the same thing many times, or many different people, can order it. So you can then think about why, this whole product, the line occurs many times. And then an invoice also contains many line items. So this is how in the real world we start to actually relate like all these things. So they give you all these examples you can read. But again, in the real world, we only use crow's foot notation. So I'll not tell you too much about this. Okay, object-oriented database. So people took the idea that every single row is actually an object, like a C++, Python, Java object, and stored this whole table as a bunch of object in disk. And then when you read it back, the system would then turn all those objects into all these columns and then populate each object, populate all the columns. So if you do that, then it is basically an object database. You're storing objects, then you're calling methods on the objects. If you say increase the GPA by 0.1, maybe there's a method called GPA.increment. You give it like a parentheses 0.01. They're really like writing C++ Java classes. If you could do that, you operate as if your whole database is made up of objects. We call them object-oriented databases. We call them object stores because we store objects on disk, okay? Okay, store means persist. So we use many different words to put things on disk. It's permanent. We call it persist or store. In Python, we call it pickling, right? Pickle. So when you pickle something, like make pickles, a pickle jar. Pickle means I store my object on disk. In JavaScript, it's so simple. I can just take my object, make a text out of it called JSON, and just put the JSON on my disk. It's so easy. In other languages, I can use more complicated, exactly CC pickle, to read and write objects. Okay, it doesn't matter how you do it. It's the same idea. You're reading and writing objects, and it's very clean because everything looks like objects. In the real world, I have a class called student, a C++ called student. Then I can turn the student's information into a C++ object, which I operate in memory, and write that exact object out to disk and read it back. So then you can do inheritance. I can have a student class with a student ID, graduation date. Then I can have a grad student class, undergrad student class, and keep going like that, right? I can do class hierarchies. It's very cool. And then I can make not just one column at a time. I can make multiple columns together, and I can make like better data types. Many things are possible. And then you can store like, graphics data with this. You can store parts for machines and, like multimedia, video file segments. You could do many cool things, but the database community is not programmers. So they hated this idea. They said, who the hell are you programmers coming to turn us all into C++ engineers? Just go away. So the world ignored it, okay? It's harder to query because, you cannot write simple SQL for columns. You have to actually write some object-oriented queries. So basically what happened is the world ignored it, okay? The world just said, go away, this is a cool idea, but you programmers can use it. Will not use it. So object-oriented database don't really exist in big quantities. So people found a happy medium, and this exists. It's a halfway marriage between objects and relations. So what happens is you can store the object on disk maybe, but then when you read it back, it'll actually become some kind of a relational table. So imagine this situation. Suppose on disk you store like a real object. Then suppose the user says, read me that object. Then the system will read the object, and turn the object into just columns of data and put all the columns of data in this column of data. The table thinks there are only columns. The relational table does not know there actually was an object. So the object gets converted to table data, no objects. And then you can do all your SQL queries, you can update, you can do what. And then when you say save, then the same driver takes that column and turns it into an object and saves it. So it's doing a two-way translation, object to tables, tables to objects. By tables, I mean just individual columns of data. So object to columns, columns back to objects. The two-way translation is a little bit slower. And so, that's the drawback with this. But both sides get what they want. Is that a wrapper about? Yeah, sure it is. Yeah, the database itself has no idea. It thinks it's all columns. It's some high-level wrapper. Correct. Exactly. So it's like a front-end programmer might actually do that. Yeah, ORM. ORM is object relation modeling. That is correct. Yeah. So OO was too much. So ORM is like a 50% marriage between OO and simply relational. Understand? Okay, good. All right. So like I said, any object-oriented like a C++ or Java program can easily access it because the program thinks it is all objects, but then it appears like a table, for the relational database. So queries can be simple because you're just doing object queries. But the drawback is because you're translating both ways. It's slower than doing it all purely as relational data. Therefore, this is really how the world has like seen things evolve. Everything was initially up here as files, actually flat files, no connection between anything. And then we don't even mention that it's like version 0 or alpha 0.1 version. Then we got beta versions, hierarchical network. And this is what was dominant for a long time. Even though there are so many variations, right? This is all one big idea. It's about storing everything like tables, okay? Again, relational entity relationship. I don't distinguish between any of these. I'm going to say they're ultimately all just table-oriented data. Tables all the way till the internet became quite popular in the late 90s and early 2000s. So from about 1970s when it was discovered, I'll tell you the story in a minute. In 85 is when really relational databases started to become used in the world. So mid 80s to mid 2000s. It's like 20 years, right? The whole time was nothing but relational databases. It's still a great idea. It did not become a bad idea. But there's now this newer thing called NoSQL. It is just very simply this. In the relational databases, it's a good idea to have a table and some other table and populate them with data, with lots of data. Just make it very simple. and do some kind of wire connection between them. It's a good idea. Everything works beautifully, only if there are no holes in the data. In other words, only, trying to pick a color here. Only if there are no blank cells. As soon as you have a blank cell, this entire thing becomes useless. All the cells are assumed to be populated, like we have no blank values at all. Then the whole SQL idea is wonderful. But because of the internet, you have somebody's, like Amazon says, give me all your customer information. And then you fill your first name, last name, you have to give them your credit card number. And then Amazon says, give me your personal email, like other than the email you used to sign up with us. Give me an alternate email ID. The customer says, to hell with that, I'm not going to give it to you, because then you'll spam me twice. And then Amazon says, give me like some alternate phone number so I can call you. No, I'll leave it blank. Give me or something else, like where you work. I don't need to tell you that. So people leave all these columns blank, right? These cells blank. So because of the internet and humans, using the internet a lot, the tables became more and more empty. And that screws up SQL, just screws up everything. So sadly, the relational tables are not very useful anymore. It is because of what people did. In the past, when banks used this and governments used this, small business used it, they would make sure that nothing is empty. Empty means null value, okay? So cells are not really allowed to be null. I mean, they can be null, but the whole machinery is wasted on null cells. So we found a new way to not care about nulls at all. That new way is called NoSQL. Now so NoSQL is nice, but in a way, relational database really is the underlying mechanism behind everything. Okay, now I want to move on and tell you a little more. Yeah, so this notion of external model is the user level of a database. So when you go look in the SOC and sign up for classes, when you go in the stars database and look at your transcript, that is called the external model, because that is what we think of data. That's how we use it, the Amazon catalog. When the SQL designer designed all those tables whose entity names we don't know about, you don't know what your transcript table is actually called in Oracle. Okay, you just think of it as the stars database. But the designer might actually call those entities something. That is called the designer's view. Like they are the ones that make the ER diagram. Okay, so you draw a nice line and you say, this is the outside world, so to speak. The inside world, the Oracle database, suppose you use Oracle as an example, then they would actually store, those tables internally in a different way. Like in memory, they might store it, not exactly as one entity at a time. They might even combine multiple entities. They might do all kinds of things internally. It's called the internal view. Even more interesting, when you write that memory out to disk, on disk, actually the binary ones and zeros, that could be a very different format. Maybe they're using linked lists. They have pointers for every single row of data, and then they're jumping between all the pointers. Like who knows how the data is actually stored? That is called physical model. Only Oracle engineers or MySQL engineers would know about like all of this, how the system works on the inside. So this is the inside level, this is the outside level. Even on the inside level, the people that work on the actual table storage and stuff, like in memory, don't really know how it is stored in the physical level. The device driver people, they would be the only ones that know this. If they change the device driver, they can even store your data on the cloud. So nobody knows that. Magically, you just throw your own business away, and you're now storing data in the cloud. And they're using some APIs to get the data, and you think nothing changed. So USC could easily store all your grades in the cloud. We would never know. So you get this independence when you have all these boundaries that you draw and say only the people below this would know that format, only the people know this format. And outside, we know nothing. So that independence is because you draw a line. Like I don't know anything about how the file is stored. So if you give me the actual transcript database as some binary files, I cannot write some C++ code to change somebody's GPA. I have no idea what those ones and zeros are, which is how it should be. We'll answer all this later. There was a question privately that said, which is faster, SQL or NoSQL? That's hard to answer because there's no such thing really. There are two different ways, depending on how much data you have or what you actually do with the data. Either one could be fast or not. There's no absolute hardcore answer at all, okay? Really, the question, doesn't actually exist. It depends on the situation, depends on the data. So for now, that's all I'll tell you. All right, you guys, so this is very interesting, right? So that was like that slide. Now I can tell you external model. This means the user level model, okay, end users. Okay, so you don't have to spend time on all this. This means if I draw you a diagram and say, here's your course catalog, and then here's your transcript, and then here's the CS department, you can loosely understand how data, passing back and forth between them. We call that the external schema. Okay, so it is just from the stakeholder. Stakeholder means the end user, the modeling of a database. It is what the user thinks of as a database. Like somebody from the research department, research administration might look at the USC, ER diagram and say, what is the table where we store how much research funds we have? You can show them a little rectangle and then they're happy. So that diagram is called an external schema. That's what most of the time we see. And that is where, for example, you sign up for a course. We call it the external model. So how do you register? Every student has a student ID there in this table. Every class that is offered, like CS585, is in this table. And a class, actually, sorry, every CS585 is here, I'm sorry. Every class we call a course. Within a course, there are multiple sections, such as, an online then section, and then section A, section B. That is why there are multiple sections. Sections is what we call class here. And you guys enroll in A section, right? The then people are in the then section. Okay, so enrollment is a separate table where a student's ID can appear many, many, many times. A section can also appear many times. Okay, without the enrollment table, it's going to be a very big mess. An enrollment table is just a real world implementation detail. Suppose you have students here, then every student is here, then this is you, whoever you are. Suppose this is the sections table, every single section for CS585 is all appearing here. So suppose this is the current section that all the students are in. So I have now, like almost 350 students. So what we cannot do is in this courses table, as a student, we cannot have a student ID column also, and somehow say this student is taking that particular section. I'll repeat that exact same section number and say another student is also taking that same section. So I cannot repeat for 350 students that section ID over and over and over. You see what I'm saying, right? This table is polluted by extra student information. Likewise, if a student is taking 5 sections, 5 different courses, I shouldn't repeat the student ID 5 times and put those 5 section IDs here because, right now in the spring term, you're signed up for 5 courses. You should not pollute the student table with course IDs. A student table should not be polluted with, section IDs. A section table should not be polluted with student IDs. Neither is a good acceptable solution. So we make a new table which can be polluted. By pollute, I mean just repeat information. So I can have as many combinations as I want between students and courses. By course, I mean a section. So Yash is signed up for CS585. Yash is also signed up for a machine learning course. Yash is also signed up for a business entrepreneurship course. The business entrepreneurship course also has some other student X. Business entrepreneurship also has Malaki. Business entrepreneurship also has some other student what. So I can just have number of students times number of sections and just only populate one new table. At the end of the term, I can just simply store this on disk and everything goes away. Such a table is called a bridge table because it is literally bridging 2 worlds, a bridge table. And the bridge table has a very interesting piece of information about it, which is if you only take one column, the student column, it is not a primary key because a student can appear many times. The student is taking many sections. Conversely, the section ID column cannot also be a primary key because a section such as 585 right now appears like 380 times. Neither one by itself is a primary key, but incredibly, this combination together, this number, comma, that number, every single row is unique. Just think about that, okay? Then that is called a combined primary key. It's called a combination key. It's called a composite key, actually. Composite, right? Better, actually. Composite key. So a composite key means more than one column can be a key. It means if you take this value and this value together, like that student ID, that section, if the student is signed up for the section, you only need the one row, there's zero reason to repeat it, okay? So the combination becomes a primary key actually in a bridge. Very interesting. So then if the designer wants in the bridge, they can have a third column that says something like, grade or something. And then when the end of the term, we can filter with letter grades, like what student, got what grade in what course, and then save that all to disk and very easily look that up in the future. So we can add more columns to that. But that combination column, which is the real reason for the bridge, is unique. It's a unique composite key. That's what this is. So this enrollment is that composite between a student and a class because neither one should contain the other information. So you put it in the middle, then you delete it afterwards. Can a type of plug be made that decides which DB? Oh, absolutely. So yeah, this student, I want to name him. There's neat questions he's asking. Yeah, you have infinite freedom to design databases in such a way that you can choose what database is used at runtime. Okay. Meanwhile, A professor like me, I'm teaching 3 classes this time, 571, 585, 580. So therefore, my name can appear 3 times in the course catalog, which it exactly does. You can go look at it. And then, a course. So then in this, sorry, I'm sorry. I keep repeating it, sorry. So my name appears 3 times in courses 571, 585, 580. But when a course generates multiple sections, my name appears multiple times there as well. And then a room such as SGM 124 can be used to teach many classes. That is why a room number can appear many times in SOC. That happens as well when we all go back to campus. The room numbers actually mean something. Right now they all say online. But you understand, right? So that is where the one-to-many, one-to-many, one-to-many is all coming from. One-to-many is one of the most common relationships between all the 3. There's not too many one-to-ones in the world. There's not that many many-to-many. One-to-many is quite common, okay? More common than the other 2. All right, so that is a conceptual model. So this was the end user model. The conceptual model is what the designer thinks of, okay? So they are the ones that actually, meaning you're asked to create this database. So the entity names you give, the relationship names you give, the column names you come up with, the data types. If all that is stored in a diagram, that diagram is called the conceptual model. Only the designer sees it, okay? Things like enrolls in, teaches, how it used to are. It's just for the designer. But overall, the entities didn't change. It's still all the same entities. Okay, and then the conceptual model should be complete, meaning it should have every table ever in the database. There's got to be some connection between like all kinds of tables. Like all of USC can be one conceptual model. Internal model is all just database specific, okay? So how does a database system take all those tables and then store them internally? So it depends on whether it's Oracle, MySQL, SQLite, what. It is software dependent, hardware independent. Thankfully, like I told you, in memory, how do you store all those objects? It is, software dependent. But then hardware independent, it doesn't actually matter, what like Unix hardware, for example, what terabyte drive you use to store, that. Because you don't think about exactly how things are stored on disk. You just say, I have some tables in memory. And so then I can change the internal schema, meaning I can use some of the memory scheme to store all my data. But then the hardware ones and zeros level, it doesn't care. That didn't change. So then that's called logical independence. Logical independence is the independence between the internal schema and the physical schema, because the last part is the physical schema. Okay, so physical schema is the internal model. So internal model is how, like I said, whatever you write at the conceptual level will actually using SQL get turned into actual objects, into actual tables in like Oracle's memory process or MySQL memory process. This is all SQL code. We'll look at it another time. Therefore, what the designer came up with, like a diagram, got turned into an actual, bunch of data in memory. Then we can now store this on disk. And that is the last level. That is called the physical level. Physical level is when the Oracle or these device drivers need to know how can I take a table and store it as the most compact. Maybe they can encrypt it. They can compress it without losing information. So it is storage media, disk drives. So you need to know the actual physical format, how things are laid out. We need lots of knowledge of low-level Unix processes to access, like read and write all the data. But at the higher levels, we don't care about any of these. It's the device driver's problem, meaning the engineer's problem. It's called physical independence. Okay. So physical independence means I can change the way I can store ones and zeros, but then the driver would then take care of taking the new ones and zeros and turning them into something higher, and then that goes higher all the way up. So you have these independences at any level to change the representation. This is why I told you physical independence is why Oracle, in every installation in the world, even on your laptop, wouldn't tell you, but silently they'll not store tables in your disk anymore. They'll silently store them on the Oracle cloud. They could do that and nobody would know. Then that's called physical independence. All right. So in the end, that is what we learned. So we learned that, there are these 4 different model levels, really, layered abstraction. You can change something at one level, the other levels wouldn't really know about it. And that's the way it should be. But the main idea was this notion of relations. You have entities and then you relate them. Now we can seamlessly jump into, the next part and then just keep going. You'll see more of what I'm trying to tell you, the ER diagrams. So in ER diagrams, entity relationship diagrams, I can tell you more about what these entities, what these relations are. In a way, it's a different chapter in your book, but it's all the same idea. Okay, so the diagram again is called the ERM, entity relationship model. It's a diagram. The diagram shows everybody what the database looks like, the end user, even the designers. But what is it actually made up of? What is the ER diagram made up of? It's made up of entities, which means table names. What do the tables contain? Columns, like GPA, graduation date, those attributes. What do you do with two different tables? You wire them. That is the relationship. So ER. That's all, okay? So entity is, again, sometimes we call entity set. My goodness, there's so many names for the same thing. Entity means the whole table filled with all the rows, which you also confusingly call entity set, because each row is, I told you earlier, was called an entity occurrence or entity instance. So many instances together, like all the students together, make up the set. So one student can be called entity occurrence. I can call them a row. I can call them a tuple. I can call them entity instance. All mean the same thing. The collection of all the students, I can call it a relation, the whole table, or I can call it an entity, or I can call it a table, or I can call it entity set. So 4 ways to say, what a table is, 4 ways to say what a row is, and many ways to say what a column is. Oh my God. You can call them columns, you can call them attributes, you can call them labels, I don't know, you can call them descriptors, you can call them members. My goodness, so many names for columns. Because in the end, columns are what contain all the data. Okay, so speaking of columns are attributes. Okay, so this is what I told you. If any column in a table, the designer says, this value is absolutely required. We call it a required column. Primary keys are absolutely required. Every student that ever gets admitted at USC must have a student ID. Otherwise, a student literally does not exist. So student IDs are classic required attribute. But you can make any column required. Like if I want your phone number, even though it's not a primary key. Like when I go fill recommendation forms to different universities, for you guys, most schools don't ask me for my phone number, which is so weird, right? Which is good. But some school will insist on actually asking for my phone number. So I put in some bad, bogus phone number. But that's an example of a required attribute that is not a primary key. They're just bugging you because they want it. In any case, you cannot leave that cell blank, okay? On the other hand, a column can be called alternate ID or alternate email address or something. And the user might choose to leave it blank. Such columns are called optional attributes. So when you design your SQL table using SQL commands, you can flag each column to be required or optional. Likewise, you can also, for every column, specify the possible number of legal values. Like every GPA in the US can be between 0 and 5. 5 because they're overachievers, that come with more than 4. GPA cannot be negative. In a company, somebody's salary cannot ever exceed $500,000. Somebody's birth date cannot be younger than 1970. You can put all these constraints, and those are called domains. Domain actually means range in math, which is so confusing. Range means the range of allowed values. In database, we call a range. Unfortunately, we call it domain. It's the domain of the data. In math, domain and range are entirely different, right? All right, so identifiers. All right, this is another name for a key. Key is loosely also a primary key. Otherwise, we never use the word key. Key, identifier, primary key, they all mean the same thing. That is one thing that absolutely cannot repeat for different rows. If a book has a book number called an ISBN number, every book published in the world, especially in the US, would have a 10, 13-digit ID called an ISBN number. That is like the primary key for that book. That number can ever change. No. An identifier is just a key. Sometimes it can be composite, okay? Identifier for now is just a key. Keys can be composite, but don't have to be. I'll give you an example right now, verbally. No, it is not, because foreign keys can repeat. Identifiers are primary keys. Again, an identifier is some column or maybe a bunch of columns where for 2 different rows or 3 different rows, things cannot repeat. Tell yourself that, okay? Things cannot repeat. Cannot repeat is a different way of saying each row is unique. Like that, but that information there is what makes that row be completely separate from all the other rows. Because anything else is allowed to repeat. See, the whole point is, in a student, right? See, I get this all the time, from like many countries, this happens. So suppose it's a student USC. I even kept, in fact, after this class, I'll put it up so you guys can just, look at it. It's fun. Suppose it's a student table, student's first name, student's last name, student's GPA, major, graduation date, advisor, school, department, undergrad GPA. Okay, so I can ask many things about a student, right? Here's a very important number called student ID. Guess what? I commonly see this even among 380 students. The exact same first name, last name. Yan Chen might be one example. Actually, I have two Yan Chens in the same section. Okay, so when I go and fill the grades, I need to be very careful because suppose one got an A, the other one got a B minus. I cannot give the wrong Yan Chen the A and B minus, right? So I need to like doubly make sure, triply make sure. I pull up the ID column and make sure that I'm giving the right person the grade. Okay, because that is the only thing that separates this Yan Chen from the other Yan Chen. All this can repeat. Okay, so in a table, everything is allowed to repeat. The only thing that it cannot repeat is the primary key. Okay, that is the identifier. Okay, so primary key a lot of times is only one column. But suppose in a different university, not USC, some small college, maybe some, Claremont Community College, they could decide you can make the combination of first name, comma, last name be the whole composite primary key. Then they should make sure that those two students have the same name. If they do, they should misspell one of the letters somewhere to make them two different students. Okay, you see what I'm saying? Suppose they choose not to make an ID like that. Then the combination of first name, comma, last name should need to be unique. If two students come with the same first name, same last name, then you can have a column called middle initial and hope that that is different. Something has to be different, okay? Then you make the whole thing a primary key, okay? Because at least one piece of information in that composite makes it different. Yes, identifier and primary key are the same, correct? Exactly. All right, so I like all this. So yeah, exactly. Bridge tables, both those columns that I put in there, like the student ID column and the course column, right? Together, it becomes a composite identifier, correct? And you can just stop there. That absolutely needs no extra column, but we can add extra non-primary columns such as the GPA for that student for that course. So short answer, Shreya, yes. Except the identifier is now a composite key because it is not just a student ID, not just the course ID, it's the combination. So bridge tables have composite IDs, exactly. Because together that information makes each row unique. But now you understand a lot about keys. I'm quite happy because it is the most, it is the key piece of information. Look at this, you got my little thumb there. Okay, so identifier is a key, sometimes called primary key. It is a key concept. That's why in English we say the word key, okay? Because the concept is so damn important. Likewise, the column value is so important. Can we drop the system generated ID column? Well, absolutely, absolutely. Yeah, so in most databases, what he's asking is every time you make a new row, automatically they'll say 1, 2, 3, 4. At USC, obviously, we never use it, okay? Your student IDs are entirely randomly generated. So we do not ever use system ID columns. So if two students are literally standing in line behind each other, suppose you physically register. So if you got a student ID of 996, it doesn't mean the person behind you got 997. You can never guess anything, okay? Okay, that's a very, very important idea. The important idea is to use to make primary keys blind. Blind means no one can guess your primary key for any reason at all. Like I said, if you're next to me and we both got, bank accounts issued, so I cannot take my bank account number, add 1, and think that's your bank account number because the account numbers are completely randomized. It's very important. If you used ORMs like Hibernate, you can choose how big is your name. Yeah, correct. So the auto DBMS is literally auto increment, plus, plus. Every row will get plus, 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 plus. Sometimes that's all you need, okay? Say you are having events, Staples stores all the events that happens at the Staples Center. They don't have to worry about IDs, they can just say 1, 2, 3. So automatic increment is enough. On the other hand, credit card numbers, bank account numbers, student IDs should not be automatically, those are critical. Like I shouldn't be able to guess your information based on, some information about me. Those are called blind IDs, and they are great. Yeah, if nobody else is going to look at your ID, the main purpose of the ID is to make each number separate, right? So plus plus will do it for you. You worry about blindness only if you think other people can exploit your database. Okay, let's move on, okay? Okay, this is probably the important thing. In NoSQL, all your NoSQL data will still have keys. We call them row IDs, by the way, okay? We just call them row IDs. We don't call them keys, but same idea. We call them row keys sometimes. You can write this down if you want. So the word row key, when I talk about this in a NoSQL database, it's really the same as like a primary key. So row key. Every row has like a key. Like your Twitter, for example, ID would have a large key. Sometimes they can take your row key and make like an API key for you, just using that. Moving on, tell me more. All right, so just more about attributes. When you draw ER diagrams, how do you actually specify those columns? Again, attributes are columns. In the Chen model that I initially told you, Chen invented the Chen model, he has this really cool little ellipsis called flyouts. It just flies out, draw a line, fly out, and all the columns are like a little peacock, right? It takes up a lot of space. It's cool, but we don't use it. Instead, we do what looks like a little class diagram. So normally in C++ classes, you write the name of the class and then you put all the members and methods underneath, right? It looks a little like that. That is what Crowsfoot model does. So in the top, you write the entity name and then column, 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 column. If the columns are bold, primary key, identifier. So this might be, again, Claremont Community College, some other little, Cal State University, where they don't have student IDs, apparently. They only have last name, first name. So if both are bolded, you need both of them to be unique together, like some last name, first name. I can have John Doe. I can have John, I don't know, Chen, but I cannot have two John Chens. Okay, I can have John Chen and Ian Chen. In other words, I can have same last name for two different people, but the first names must differ. Or I can have the same first name, but last name must differ. Because with the first name and last name are the same, how can you tell those two people apart? You cannot. That's not allowed. Okay, so Crowsfoot is very simple. Maybe for your homework, this is what you would do. Yeah, USC email IDs are very interesting. They try and give you your name if possible, but otherwise, if two people have the same name, then you start to see things like .666, right? Although that's the mark of the devil. So if they ever give you .66, ask for something else. Don't want to be the devil, okay? But no, they put random IDs. In fact, if you go to our course, I think that's up here somewhere. Somebody, I think, has like an ID somewhere. Yeah, that one. Maybe there's like a couple of different Richard shoes. So this one got 47918, totally random. This one. That's interesting. That's such a Tamil name. Saravanan Manohar. For some reason, they thought it was too long. I don't know. They gave you like a blind ID there. I got pretty lucky and I grabbed my small little name there. Yeah, because I never gave it out to you. There's no 404 error. Okay. Homework 1 involves the things that I'm telling you as we speak. So no cart before the horse. Okay. There's no 404. That's funny. Okay. The rest are just amusing, which I like. It's good to be funny. All right. So attributes, again, see, it's all about the columns. Okay, column, column, column. Columns are damn important because columns are what ultimately carry all the data. All right, so a composite identifier, sometimes called a composite key, is last name, comma, first name. That combination must be unique. Okay, that's an easy concept, right? Or sometimes last name, comma, first name, comma, middle initial. Because I think that too many people have the same name. So it's all about making a unique primary key. This is a very different idea. Some columns can be called compound attribute. Sadly, in our textbook, they call it composite. It's like weird, okay, that's wrong. We should call it compound attribute. A compound attribute is very simple. A compound attribute might look like there are 3 different columns, okay? But together, internally, the database thinks of them as one composite attribute. The easiest example is RGB. There are columns called RGB, and I store a color value between 0 through 255, 0 through 255, 0 through 255. Suppose you're Nike, and then Nike says, what shoe color do you want? Pick from a color picker. Well, I'll pick. Then they store the color that you picked, okay? And that color combination is for the shoe that you want. See this, like right here. That combination, right, is exactly RGB. Some other combination is RGB. So RGB together is what ultimately give you, any unique color in the world. Quickly, how many different colors are there? When you have RGB that can be between, R can be 0 through 255, G 0 through 255, B also 0 through 255. So 256 different values possible for R, G, and B. See here, they all are, right? If you give me like all the time in the world, I can give you all the 16.7 million colors right there. So what is the number that I just named? 16.7 million. It is 2 raised to 8, right? Times 2 raised to 8, times 2 raised to 8. 2 raised to 24, you guys. So 2 raised to 24 possible combinations exist. That is roughly 16.7 million. Okay, so that RGB is individual values, but I can store them in the table as if they're individual. But internally, each combination of RGB is treated like a compound attribute. So I can have a compound attribute called color, which my 3D printer understands or something and prints your issue. But the database calls them as 3 columns. So such columns, when they can be compounded, X and Y and Z for the vector, the direction in which I launch my missile, I can have 3 spatial values called X, Y, Z, and I press the button, that vector in 3D space is where the missile is going to go off. That can be a compound attribute because it's called launch vector. Now, what direction should I orient my bucket? Simple attribute is the opposite of compound, where you cannot subdivide anymore. So like a last name is a simple attribute, GPA is a simple attribute, your salary is a simple attribute, simple and compound opposite. How? That's weird. Single valued attribute, you eventually want every attribute, if possible, to be single value. Your GPA column contains exactly one GPA, right? You don't have multiple GPAs, there's no such thing, it's weird. Fake news. So in principle, every column and every row, every cell really, should have exactly one piece of information. You cannot pile on multiple pieces of information at all. But for practical reasons, sometimes you want that. Not simultaneous, the same information overwriting each other, there's no such thing, but maybe for historic reasons. Suppose this is CNN.com. This is all the websites in the world, right, that have news. So every news site, BuzzFeed, College Humor, PBS, NPR. Maybe there's a column called headline. Exactly what does the current headline say at CNN? I can go find out. Every hour they change, right? Suppose you want to store all those headlines and track over time, what those headlines said. That is called a multi-valued attribute. This morning it didn't say that. This morning it said something else. It said the Republicans did not want to impeach Trump. That's what it said. Okay, so if I store all of that, right? If I store all those headline strings, I can put some other timestamp information next to it, right? But the idea is somehow it's a multi-valued cell. I can't stop. So, all conversations end just when I said that. If you want to store many values in the same cell, it's actually logically impossible, but we can find ways to do it. You guys crack me up. Okay, then that is called a multi-valued attribute. So for now, that is all I'll tell you. In reality, it shouldn't exist in the world. But for all sorts of reasons, it does exist. And so in the simple table mechanism, in this relational table mechanism, there is no way to store more than one. It's like a variable. You assign a new value to it. Guess what? The old value is gone. But we can create extra tables and actually store like as much information as we want. So we can implementation-wise make it work. But in reality, in concept, a cell can only have one value. So new value should overwrite the old value. So just tell yourself that, okay? Okay, so then if you say these are fascinating, can you tell me more about columns? Because it is all about columns. In NoSQL also, there are columns. It's all about columns. Because columns ultimately are what, store everything. This gives you, entities or attributes and all the things I told you what. So then an attribute gets values and we call range domain, and then social security numbers are unique in the US. Although social security numbers, unfortunately, are not blind. People that know what to look for, they can know what county in what state issued your social security number. If they want to find you, they can go live in your city and try and track you. It's a little creepy, okay? So it is not as anonymous as you think, unfortunately. But that's how the US government decided. Likewise, your phone number, the area code can tell you, roughly what area you're from. It's also not blind. Okay, simple attributes are, atomic. Like color is not RGB. What if color was a string, such as orange, blue, cherry, lime color? You need to pick from a string. Then it's atomic. Age is atomic, salary is atomic. On the other hand, compound is, more than one. What if I have something called address, which is compound? And I split that up into street, cities. This way informs the bug you, what is your city, what is your appointment number? Because I think that every single address should have that. I can make a compound name as well and make the first name, middle name, last name. It's like almost a wrapper, like a wrapper object. Okay, that's what a compound is. Multi-valued is very different. This is a good reason to have multi-valued. What if somebody has more than one degree, so you have a degree column, and how are you going to put BS, MS, PhD? You cannot have a single cell. I need a separate table, okay? That is the answer. So the short answer is, if something doesn't work for you, make a new table. That's always the answer. Yeah, one more level of indirection. In computer science, we have a joke. Any problem in the universe can be solved by one more level of indirection. So the level of indirection that we can have is I'll make a new table with my ID, and then a skills column. And then I can make some kind of bridge table and I can, to my heart's content, just repeat, CT, BS, CT, MS, CT, MS, CT, MS. Hey, that's where I got all those degrees. So I can force someone to make a new table for me. All right, so then that is really how you have the multivariate problem solved. Just make a new table for it. All right, a derived attribute is a column that you don't have to physically store on disk, because if I told you today's date, or today's date, if you gave me a birthday, and I can subtract one from the other, I'll know how old you are. I don't need to store both your birth date and also your age column. It's pretty silly. Age can always be simply calculated. So those are called calculated columns. Derived attributes, you can derive them. So multivariate attribute, right? Yeah, sure. Yash has got like all kinds of cool things to tell you guys. Key is really the only one, a column or a bunch of columns where two rows this is wrong, right? Not two entities, two entity instances. See that? Where's that coming from? Emory. That is incorrect, okay? Because entity is the whole table. What they're saying is no two different rows. So please say rows or entity instances, or say entity, what do we call it? Occurrences, yes, but not entities. Simple can be broken down into single, yeah, correct. So simple, well, no. I mean, simple cannot be broken down. So please don't say that. Simple and single are basically the same, okay? So don't make it more complex than it is. If you can maybe express it as smaller, then you call it compound. Otherwise, it is simple. Like RGB. If color was RGB, then I would call it a compound. If color was a name I have to pick from like a drop down, it's not compound. Okay. Names can be simple or compound. It depends on how you make it. If I make separate columns called first name, last name, and leave it at that, each one of those is simple. You cannot break it down further. But if I pretend I have a name column which is compound, then yes, it has things called first name, last name. All right, you guys, they're basically the same. Yes. I'm not reading all that, but I should. What else? Null, yeah, null. Just forget nulls for now. But nulls basically are a big no-no because nulls actually mess up things like averages. Anything. Null just like waste processing. Okay, I didn't want to spend too much time on this. Just FYI, many things I tell you FYI. Okay, a little behind. What the hell? All right. So multi-values. So conceptually, you can have multiple values in one row. A classic place where that happens increasingly in the world is cars. When Ford made cars, and every single car is made by Ford, each car has a row from the Ford Motor Company. Every single car in the world is separate from every other car using a primary called the vehicle identification number. This is what's in your registration. This is what's also in the windshield of your car. When a car gets into an accident, that is the information that is used to enter the details of the accident. When you buy a car from somebody, that is what you should check. It has the entire history of the car. There's only one car in the whole world with that VIN. Even if you destroy the car and you throw it away, you chop it up into parts, that VIN cannot be reused because it'll cause chaos, okay? Okay, so that's VIN. Cars can have a model, make, the year that was made, the car's price. So every car in the factory is going to have all of that. Now comes a very interesting attribute called car color. In the past 100 years ago, the car color was black. Ford said, make a car in any color you want as long as the color is black. Okay, the guy loved black color. He said you cannot have any other colors. But Toyota can now have white cars, blue cars and red cars. But there's more to it than that. So now your car can have actually a color just for the tire wall. The tire wall can have this nice red color. Your car can have a separate color for the sunroof. My car can have separate colors for the headlight, the rims, right? So there's no longer just one color. My car seats can have different colors. Therefore, this notion of one color column goes away. So we call this a compound attribute. Sorry, we call it a multivalue attribute. Somehow we pretend that even though commas are not allowed, I'm going to put many commas, okay? So we can do this with implementation. I can implement in many different ways. But conceptually, I'm allowing many commas after all. Then we call that a multivalue attribute. Okay, so how do you then how does a designer convey that intent? In Chen's notation, have an extra circle, make two ellipses, and such columns become multi-valued. Very interestingly, in the crow's-foot model, there's no way to tell. It's a very interesting, aphorism that says, you cannot tell which way the train went by looking at the tracks. Or just stand at the tracks and look at it. I have no idea, right, where the train went. The tracks don't tell you. Likewise, the car color, column in this diagram notation does not tell you if it is single valued or multi-valued. You have to read some extra documentation that comes with it, okay? Okay, so different diagram notations have different strengths and weaknesses, that's all it is. Okay, so in crow's-foot notation, anytime something is bold, okay, if you make something bold in crow's-foot, so bold is required, not null. And bold can be not just the primary key, but also any column. If you make some column bold, it means, the designer says even it might not be a primary key column, but you cannot leave it. Like a car's model, right? A car's make. They're not primary keys, but you need to know Toyota Corolla, right? No, Honda Civic or Honda Accord. You have to know. Therefore, you would make them bold, in crow's-foot. And then in crow's-foot, if you underline something, primary key. Hey, cool. So again, more about attributes. When you have multi-valued attributes, if you hold on to, maybe when we do the discussion, I can ask you exactly how you would make up multi-values. Like for the car example, If I give you a car can have up to 4 different colors: headlight rim color, tire wall color, seat, which is interior, and then like sunroof color, and maybe the body color. How would you make it work? You need to tell me you make a new table. So let's wait for that, okay? So I'll move on, but it's possible. You can make this one solution. There's actually more than one way to do it. Please think about maybe a couple of different ways in which you can create new tables. You're allowed to create new tables to store multivariate attributes. This is the kind of thing I would ask in the exam, something that you would think about, and then know what to say. Okay, a derived attribute is very easy. It is a column that just exists in only like a name, but no storage, because you can very easily just calculate it. Age is the best example. I can just subtract your birth date from today's date. I'll know how old you are, approximately. Obviously, if today is your birthday, things can change, but overall, I can find out. All right. So then how do you depict, how do you tell, the world that something does not have to be stored? You would make dash, dash, dash. That way, that means you don't have to actually, store it, you can calculate it. Okay. Then in the crowfoot notation, we cannot tell. Okay, these are not derived, by the way. So there's no separate way to say derived or not. You have to read the documentation. If all else fails, RTFM. Okay, this is always there, right? That's right, the right documentation. Cool. Okay. So we don't worry these days about notations. Notations used to be a big deal in the past, but now everything can be, documented easily. All right, so this notion of deriving attributes versus calculating an age for every single person and storing that on disk and wasting disk space. When would you quickly calculate age? When would you store on disk? It's classic memory computation trade-off. In the world, we always trade off between memory and computation. What do you spend time computing versus, what do you don't want to compute, but waste storage space? If you store it, you don't need to calculate it. What if the calculation was so complicated? What if the calculation was how much principal, money do you have, you deposited? Then what is the interest rate? And so today, how much the actual bank balance? Say it's an exponent calculation, and you're doing like stock trading or something based on that value. You don't want to keep calculating the exponent every single time. You would lose like valuable milliseconds. So that database would say, when I'm not doing stock trading, I'll update that information so it's always correct. Meaning I'll store that value in an extra column so that when I want to go look at it, it's right there. So I save on computing, but I waste on disk space. On the other hand, why do you not want to store it? Because you can save disk space, you don't have to waste disk space. So they're opposite of each other, okay? So why do you, want to, like when storage, obviously what happens? What is bad about storing? Well, you're wasting memory. And then you have to back it up, and you can go out of sync and like on and on. All right. So, there's not 4 different, there's only really 2, okay? It's a classic trade-off between when would you compute, when would you store. Okay, relationship. This again goes back to 2 tables. When you have 2 tables, then the whole one-to-one, one-to-many, many-to-many, now I'll tell you a little more. The 2 participating tables, the other tables for which there's a relationship, like a relationship between a student table and a course table, a relationship between a painter table and a painting table. The participants are things like painters, paintings. It's pretty simple to call participants. Now, this whole notion of connectivity versus cardinality. I can tell you why we saw things like 1, 1, okay? So when we join 2 tables together, I think there's a picture that's coming, like these numbers. When you join 2 tables together, there's 2 different things you talk about. One is called connectivity, and this is what I already told you: one-to-one, one-to-many, many-to-many. All that is called connectivity. So connectivity only has 3 possibilities. When I give you 2 different tables, they can have a one-to-one relationship. It means one row on the left table will, will participate exactly in a relationship with one row on the right-hand side table. Then that is a one-to-one participation, like here. Any row here, meaning, any primary key really is what a row means from now on. So any primary key here, the person or the product or whatever, are participants, the rows are the columns, always rows, you guys, okay? Well, no, wait, a participant in this case is the entire entity. So when I say one-to-one, one-to-many, many-to-many, you're saying what is the relationship between one entity with another entity. But in reality, if you look within, you are talking about rows. So one-to-one means this one row, how many times can it relate, like how many rows can it relate to? If these are employees, and then if these are stores. If you're talking about a manager relationship, then one employee is going to act as a manager, and that employee manages exactly one store, the store. So This row, this ID can occur only one time. They cannot manage many stores. That's called a one-to-one. So then the relationship happens to be between rows, okay, ultimately. All right, so that is the whole one-to-one, one-to-many. A student can, play many sports, or a sports can be played by many students. That can be like many to many. That is called connectivity. Cardinality is all about putting limits on these, putting limits on this connectivity. But what does one-to-one really, really mean, okay? Can I have 1 to 0? Like, can a store run without any managers? In the Trump administration, so for 4 years, many positions were not filled. He just left them empty. You could just blink. There is nobody's name. So these are all like federal employees. That column is blank. Nobody's managing the department. Or he made what are called acting heads of something, acting head of, USCIS, acting head of DOJ, acting head of, EPA. Those are not real either. They're fake. So those column names are empty. So then that cardinality for that is 0. Okay. I'll tell you exactly the 0, 1. But sometimes you can have a cardinality of 0. One-to-one does not mean that must exist. Likewise, if I have one to many, one professor can teach many courses. I put a limit of minimum 1 course, maximum 3 courses. USC would tell me, every term you need to teach a course. Which course are you going to teach? Or you cannot teach more than 3. Don't become greedy. Give a chance to other people. That limit of 1,3, it's called cardinality. A different school might say occasionally a professor does not have to teach anything. They can just participate in research. Then the minimum can be 0. Then the professor's name. Suppose these are a list of all the professors. These are all the sections being taught as we speak today. Then my name does not have to appear anywhere. If there's a rule for USC that says the professor can occur 0 or more times. It is either 1 or more or 0 or more. That is usually what the whole minimum limits are, okay? And maximum limits happen to be real numbers, like 5, 2, 3. Okay, now I can tell you exactly this minimum, maximum. What is a good example? A good example is this, professor class. First of all, connectivity is very easy, okay? Okay, so there's 1, 1, 1, 4. What this means is, first of all, I'll just read this part and come back to it. Cardinality min max for all these 3 variations. Cardinality means, let's take 1, 1 as an example. In a one-to-one relationship. Suppose it has 1 to 0 as a cardinality. What that means is one of these can participate in 0 of those. Like one employee doesn't have to manage any store. It's called 1 to 0. Likewise, 1 to m cardinality. Suppose you take the 1 to m relationship, like 1 to many. Like a professor teaches many courses, that's 1 to many. The minimum maximum can be 0 or 4. So 0 means I don't have to teach any course. 4 means I have to teach maximum courses. So min sometimes is lower value is called modality. This value is called modality. This value is called cardinality. We call the whole thing cardinality, but sometimes it's very confusing. Only max is called cardinality. Min is called modality. And then this is the most important thing. The inside symbols are the minimum, outsides are the maximum. Minimum, minimum, maximum, maximum. Wow, what does that even mean? A class should have a minimum of 1 professor that teaches it. A professor should teach a minimum of 1 class every term. Okay? This professor's minimum is here. Class's minimum is here. A professor can teach a maximum of 4 courses. Okay? Again, maximum goes here. A course can be taught by maximum 1 professor. Because courses are not shared, by the way. Most of the time we teach a section by ourselves. So min and the max is 1 for a class. That means USC might say a course, if it is offered, should be taught exactly by 1 and only. 1, 1 means 1 and only. That's really what it means. Okay. So again, minimums go inside, maximums go on the outside. And sometimes the minimums and maximums can be the same. And in which case we call it 1 and only. Cool. Okay, now you know a lot about all this. So please read it. Okay. Cardinality. So I told you the word cardinality has 2 meanings. The entire thing is called cardinality, min and max. But sometimes only the max is called cardinality. To confuse you even more. If we tell you the USC student transcript has 40,000 students, meaning there are 40,000 enrolled students, that number 40,000 is called the cardinality of the whole table. FML, right? That's exactly what database terminology is. This confuses the hell out of you. So don't be confused. Cardinality, in this case, is entirely, it's nothing to do with mins and maxes. Like, how many objects are in my table? That's called cardinality, all right? Yeah. Okay, number of columns. But why? For no good reason. I use that phrase a lot in my life. Why? No good reason. I cannot give you a reason. It is what it is, right? Go ask them. Seriously, no good reason. Okay, so if a number of rows in a real table is called its cardinality, there's also a number of columns. How many columns do we store per student? And then we can call that the degree. The hell? Table's degree. Simply the number of columns. So table's cardinality, table's degree. In a real table, okay, not in a design table. Like how many students do we actually have? And what does the table actually have? Okay, one last time. Going back to the whole connectivity idea, we take the one-to-one, one-to-many, many-to-many, and we call that cardinality ratio. Who the hell comes up with all this? Not me. Okay, but then you're going to find all these, in real life and in textbooks, and don't be confused. Okay, one last time I'm going to tell you. Connectivity is very easy. One of these relates to how many of these on the right-hand side? One-to-one, one-to-many, and if left-hand side also relates, many-to-many, it's easy. Cardinality has mins and maxes, but what does the one-to-one really mean? Can I have 1 and 0? That is these lower numbers. Usually they occur in pairs because min, max. And then you read it backwards, meaning a class has min 1 professor. A class also has max 1 professor. A professor teaches min 1 class. A professor teaches max 4 classes. If this was 0, then that means the professor does not have to teach at all. Okay? This would still be 1-1, because if the class was ever taught, it'll have exactly 1 professor, right? A implies B, B doesn't have to imply A, that sort of thing. Right. Wow, let's move on. Now we come to another very important property called existence dependence, existence independence between two tables. So a table says to itself, can I be independent in the whole world all by myself, like a grown-up? Hey, this adulting thing. Or am I always dependent on somebody else in the world? That's a very important question in real world. That kind of a notion of tables existing all by themselves is called existence independence versus existence dependence. So I'm going to tell you what those things mean. All right. Existence dependence means those words. That table, it's all about tables existing. A table can exist in a whole database, meaning in a whole ER diagram, only because of some other table. If the table went away, then this table I'm talking about also cannot exist. Or more correctly, a row in the table cannot exist. Suppose this is the employee table. We use the employee table a lot. USA has employees, Amazon has employees, everybody has employees. There's the employee table, where every single employee has unique ID, employee ID column. And then here's me with an ID of 6 right there. Suppose here's a different table altogether. It is called the table of dependence. Dependence means your spouse, your children, other people that are dependent on you, mostly for insurance purposes. Dependence table. The question is, so I have a wife and 2 kids, okay? My little twins, Josh and Vicky. Then I have 3 columns. The table, so employees have all kinds of dependencies, thousands of rows here. But these 3 are my rows, okay? Okay. So then there can be all kinds of primary keys. We'll get to that in a minute. In the easiest case, just number them 1, 2, 3, 4, 5, 6, 7, 8. Suppose there are 100,000, then the 40,000, people that work at USC have 100,000 dependents. It's possible. But then this is me, okay? I'll have an ID here, a foreign key ID called employee ID. That is going to say 666. And this will be my wife's name, my kid's name, first name, last name, their birthday, what kind of insurance coverage they have. But the key is the fact that it says 666. Now what will happen is these people get coverage. They can get the dental for free, the vision for free, the hospital visit for free, because I work at USC. USC has amazing medical plans, just FYI. The best in the nation. Okay, so we're lucky. But if I quit USC and I go work at Caltech, then that is pretty cool. Caltech says, yeah, it's easier. But these 6 cannot continue to exist in the USC database, because if they do, then say Caltech also gives us nice healthcare. Then I can go to either hospital and get double the healthcare, right? That should not be possible. So then in that sense, this is a dependent entity because of these primary key, foreign key relationships, okay? That is what existence dependence means. This row really cannot exist without this row. So if I go away, then some automatic or manual scheme should remove them. Otherwise, it's not fair, because other people are paying for this. That is the notion of the whole existence dependence. But there's much more to it than what I told you. Okay, so an entity, the whole table as a whole, can only exist because, in other words, dependents are called dependents because they depend on the primary employee. So the whole table does not have a reason to exist if there's no such thing as employee table. So that is one concept to keep in mind. But I'm going to tell you a lot more. What does existence independence mean? This means that entity that is existence independent from all the other entities does not depend on any row, any key anywhere else. It can have a table full of data all by itself. If such a thing happens, and it's quite common in database design, such an entity that is independent is called a strong entity, or we call it regular entity. So what makes something strong, aka regular? I'm going to tell you. Okay. Again, follow along carefully. It's not a hard concept, but don't assume like what you think it is. Just wait till what I tell you it is. Existence independence implies strong. So that is what strong means. That is what existence independence means. It means I'm not dependent on somebody else. Okay, but suppose you say existence dependent. If I tell you the dependence table at USC is existence dependent upon the primary employee table, that does not make this a weak entity. Strong and weak are not opposites. It's a very crazy concept again. Strong and weak, like weak is not the opposite of strong. Strong means completely standalone, but weak does not mean no standalone. So look, what does that actually mean? Why are you telling me that? Because I'm going to tell you. There's one more idea we need to look for. It is called relationship strength, which I haven't fully told you about. So only when something is existence dependent, and also like relational strength weak, then the whole entity, we're going to call it weak. So let me give you a simple example, and then it'll all become very clear. It's an easier concept than I make it out to be. Okay, so first of all, going back to existence dependent, an entity B, like dependent table, children table, spouse table, is existence dependent on another entity A, such as the employee table. If a row in B can only exist when its foreign key is not null, like Sati did not leave USC, then that is called existence dependent. So it's very clear that in this case, the dependence table is existence dependent upon the employee table. But I'm not calling it weak or strong. Okay, I'm not calling it weak or not weak. That is a slightly separate concept. Such as if A is an employee, B is dependent. It's the exact example that I have here. Then a child in B can only exist, meaning there can be a row on the table if the dad or the mom works, they're an employee at A. But it does not mean B is a weak entity. So we shouldn't just look at this diagram and go, wow, this is now a weak entity. It is not. What makes something weak? I haven't told you yet. Okay, so what is weak or what is strong depends on a new idea called a relationship strength. So what the heck is a relationship strength? It is really all about this little part that I quite didn't tell you, okay? Okay, so I kind of glossed over on purpose to tell you what could be the primary key for all of this, okay? It turns out that the primary key for all of this can actually be expressed in two different ways. Maybe it's worth drawing this again. Okay, I'll go for like a smaller stroke this time. Okay, so there's two different ways in which you can specify primary keys. One is a composite primary key. The other one is actually like the atomic primary key. It's very interesting, right? Okay, so watch this. Again, this is good old employees. This is dependence. Again, dependence means, I should just say spouses and children, okay? I'll just use a different term. Spouses and children table. Okay, so what should be the primary key for this that makes this column unique? Again, some employee here was, employee ID 10. And then 10 is allowed to occur multiple times. Like say 10 occurs in two rows, let's keep it simple. So this is the employee ID. This is also the employee ID column. So the column is pretty much a foreign key. So 10 is here, and 10 is also here. But what is going to make this unique? On the one hand, I can number this entire thing sequentially and make this 1, 2, 3, 4, 5. That is one way to do this primary key for this SC column. I can call this SCID, spouse, children, table ID, SCTID. Just simply numbering them sequentially is one way to do it. And that will make sure that 110 and 310 are obviously different. So now everything works. But we can do it very differently. You know how we can do it? We can make a composite column composite key made of two columns. On the one hand, I can bring the employee ID number back here again. That same employee ID. And I'll remove it from here. Remove it. And I can have a new column called dependent number. So now 10 spouse is 1 because 1 is like spouse name. 10's first child is the second dependent. 10's next child, like my wife, twin. I could make that unique, right? 10.1 is not the same as 10.2, 10.3. That is also a way to specify primary keys. How you do it is what makes it strong or weak relationship, right? That is so cool, okay? So that's what this says. So weak, non-identifying relationship. The primary key of the related entity, meaning the primary key of the SC, spouse children table, does not contain a primary key of the parent. That is what I had before. When I just call all these 1, 2, 3, 4, 5, and I make this foreign key, this 10 is not anywhere here. That is exactly what makes it a weak. It's called a non-identifying relationship. Weak is a good thing, by the way. So weak means no connection between tables. Just like in class construction, you don't want classes to be tightly coupled to each other. You want loose coupling. Within a class, keep all the information together, tight coupling. But in between classes, you should not link them. Friends, hey, you and I are double quotes, friends. That should not happen, okay? Sadly, in C++, there's a weird idea called a friend relationship, which can actually go around object orientation. It is a way to break object orientation. It's not a good thing. So friend should not be used in C++ design unless, the design is so bad, you're forced to use it. But otherwise, friends are not good because, you're like going, through the, hierarchy and randomly making things like connected. Likewise, a weak relationship is a good thing because this primary key should not be tied up with the primary key. On the other hand, if for some reason the designer chooses to do it this way, I want my employee ID and some new 1, 2, 3. What this means is for a new employee, suppose there's an employee 20, that person can also have 21 and then 22 and 24 even, I keep going. You see, right? Again, that combination is unique. The 1, 2, 3 is not unique, it repeats. The 10 is also not unique, but the combination becomes unique. If you do it like that, that tangles up these two tables hardcore. Then we call it a strong identifying relationship. Okay, so guess what makes this a weak entity? It's a weak entity if, first of all, logically speaking, this should not exist at all, meaning it's a dependent entity. And also, exactly, it has a strong bad relationship. So a strong relationship and a dependent entity is what makes this weak. On the other hand, if it is only existence dependent, but it is not strong like this is not a weak entity. Then you ask me, is a weak entity a bad thing? Like, in other words, if I do it like this, is it really a bad design? Not at all, okay? It is just something to keep in mind, it's just a design feature. So there's no preference between a weak entity and a not weak entity. It's no big deal, but just be aware that it is weak. I'll tell you a slightly different answer. In this case, suppose I make all these blind IDs 1, 2, 3, 4, 5, and it is not a strong relationship, meaning this is not a weak entity. It is slightly better because suppose I leave and then these people still continue to exist, right? It won't kill the database, okay? On the other hand, supposing I do weird things like, if I, what is the best way to put it? Basically, if I go and look here and then this is null, then that's totally okay. Like suppose I leave and then we go and delete these cells. We don't delete the whole rows. Suppose you only delete these cells. So null cells are okay, right? Because it's not a primary key. On the other hand, if I delete this, then you're forced to delete the whole table. So what if USC says, even if an employee leaves, I still want to hold on to all the dependent data. So I want to go back in history and analyze, how many dependents people had. In this idea of having independent IDs, that's okay because I just killed this little cell. And then, this can still be stored in memory. But on the other hand, if I make it strong like this, and then if I leave, and then this is now a hole, then the system will automatically delete this whole row. Then the information is gone forever. So in that sense, a strong relationship is a slightly bad thing. Okay, so what is a weak entity again? Here's the answer. Weak entity is something that is two different things at the same time. It is existence dependent. A row here is only conceptually logically there because the row is hopefully connected to somebody here. That is one condition. Second condition, the primary key here is also a part of the primary key. When both of those are true, it becomes a weak entity. Clear? On the other hand, if the second thing that I told you is not true, meaning it is existence dependent, but the primary key is not this, it is this, which is 1, 2, 3, 4, 5. Then we don't have this situation anymore. It's not this, it is this. That does not make this weak. It only makes it existence dependent, which comes from the business logic. Obviously dependents have to be dependent. All right. So weak is one more thing. All right. Makes it weak. Are there any particular instances? Yeah. So like I mentioned, the only thing is a use case where you think, can this row totally be deleted? Would that affect your database or not? Can only strong relationship? Yeah, exactly. Well, a strong relation and also existence dependent. Strong is just simply I'm reusing primary keys, but supposing this table can still survive all by itself, then that is not weak. It is weak if the whole table cannot exist without this table and I make a strong connection. Together they make it weak. These are the questions that everybody from Amazon to Google to Facebook ask you, okay, or Oracle asks you. These things come up more than you would imagine. And people get so confused, and it's not that confusing. Just think about it. All right, so what about a course and a class? So now a little bit more familiar. Supposing a course like CS 585. What if the primary key is not composite but contains employee ID? Yeah, sure. It doesn't matter, what the primary key is. If you stick it also here and you make the tables tangled up, it still has a strong relationship. Yeah, it's fine. If this is a string, you can put the whole string in here. Or if this is a composite, you can stick the whole composite here. It is the idea that the primary key here is also a part of the primary key here. That is what makes it strong. On the other hand, no matter what all this is, if the primary key is simply just a little foreign key, then none of this happens. It's not a strong relationship, all right? Okay, so a course such as CS 585 can generate multiple sections like 01590, that's where you guys sign up for all the time. So then USC has a choice. When they make multiple, by the way, a section like, the section you sign up for, you cannot sign up for it unless CS 585 is offered in the first place, correct? Meaning these sections become dependent on the courses. So no course, no section. So clearly existence dependent. But now the question is, what are we going to do with the primary keys? The primary keys are just simply separate course IDs that never repeat throughout USC. So if in the SOC, what is the easiest way to reach the SOC? It is right here. I'll just show it to you. If our course section ID is not repeated for any other course, then that's one way to do it. You see what I mean? These ones. So suppose this ID is unique. Okay, suppose it is unique throughout all the courses. Then that does not make this a weak entity because this thing is existence dependent on CS 585. But these are unique primary keys. Okay. On the other hand, suppose we don't do it like this. Suppose we say CS 585 space 1 first section, CS 585 number 2, CS 585 number 3, CS 571 section 1, CS 571 number 2. Then that is when the primary keys become tangled. All right. Literally, if I say CSCA 580, if I took the thing up here, sorry, what is a good way to do it? Here. No. Well, there's somewhere, yeah, like all these have numbers, okay? Like what I'm trying to do is just make a little number for it. Yeah, that course number. Suppose I make a composite key with that course number followed by 1, that course number followed by 2. Look at how many courses. Wow. Rather than do it like this, suppose I say CSCA 1 or 2 and then 1 or 2. Then that makes it a strong relationship, all right? So USC does not do it like that. So therefore, for us, this is not a weak entity. I used to teach that class, but I never taught that many sections. It's crazy. I taught 3 sections at one time and I went nuts. Why? So that example, you understand? Oh, I think I went too far. Such a thing as going too far. So let's go back here. What's doing here? Okay. These are all things you understand. Very cool, very cool. Cool. Yes. All right, so once again, if this section ID was all separate, like USC does it, then that does not make this a weak entity. It only makes it a dependent entity. On the other hand, the way to make it weak would be take this primary key like CS585, stick it here, and also have one more column that says section number, 1 to 3. That is what is done here. So the class is not weak, although class is absolutely existence dependent. On the other hand, what makes it weak? Literally, the primary key is going to change. See that? This course code CS585 is also showing up here. But now the section numbers are not things like, 20980. It is simple numbers like 1, 2, 3. If CS585 is offered 2 times, the section ID would be 1 and 2. If CS104 is offered 5 times, sections would be 1, 2, 3, 4, 5. So by itself, the number 1 would repeat many times. Likewise, by itself, CS585 would repeat many times, once for online, once for them. But that combination would not repeat. If you do it like this, then that's a strong relationship. And it's also a dependent relationship. Together, it makes it weak. Cool. So class is now weak because it is existence dependent, like no sections without courses, obviously, and also a strong relationship. What makes it strong? That makes it strong. Previously, we didn't have that. Previously, we had separate IDs. Not really. No, there's no equality there either. The only thing that is true about everything that I said is strong relationship plus existence dependence equals weak entity. No other equality holds, okay? Yeah. Cool. Right. Funny. So class is weak. Class was not weak, class is weak. That's really all, okay? So why was class not weak? Because of this. Why does the class become weak? Because of that. That's the only thing I want you to get from this. Strong entity, yeah, exactly. Okay, so if something is entirely existence dependent, right, then you can talk about weak or strong, even though the primary keys might be tangled up, like I told you, if this table can, some other example, there's no big relationship, like a row here can exist even if this totally goes away, then that kind of, thing can be like strong entities. We don't usually talk about strong entities. We only talk about weak entities. We talk about strong relationships. And that comes with a consequence, because like I told you, if this row disappears, then because that is part of this primary key, this row will also disappear. You cannot hold on to this row with like a null little hole. On the other hand, if I made this a foreign key, then if the foreign key can be null because this row went away, I can still store the rest of the data with just that little foreign key being null, so I don't lose the data. So in that sense, not weak is slightly better than being weak. You understand, right? All right, so one last time, weak entity is 2 conditions. First of all, you should only, your whole table should only exist because of some other table. And then this is the thing that I showed you last. The primary key of your dependent table becomes partially or totally. Usually never totally, okay? Like what we mean is you borrow the other one's ID and also add 1 extra column. And how do you, like, which do you choose? It doesn't matter, just pick one. So again, a weak entity, 2 conditions, this and also that. So if an entity is weak, immediately it implies it is existence dependent, agree? Because weak comes with 2 conditions. But if I only told you something is existence dependent, you cannot assume it is weak. So A implies B, but B does not imply A. In fact, not B implies not A, okay? You can say that. If somebody is not existence dependent at all, then there's no way in heck that would be weak, okay? Why am I just saying all this to you? It is this. So if something is a weak entity, it necessarily implies that the table has some kind of dependence. Therefore, all that you know is if the table is not, weak in the first place, and it's also not existence dependent, sorry, A. So not B implies not A. Cool. Neat. Yes, and then told you all this, and then a weak entity. Yeah, so weak obviously means 2 things, and one of them is a strong relationship. Strong relationship has 2 other words: owning relationship, identifying relationship. We use too many words for saying the same thing. My friend Lurong, she used to say that to me. Too many words, you're using too many words. So that's really what it is. Don't talk too much. She said, don't talk. Okay, so removing, controlling, owning entity. Yes, duplicates. All right, so if you ask me, then what is weak, right? If you remove that, so suppose you throw the whole column away. Suppose you go to this, right? So why do you call it weak if this happens? Because if you go and delete this whole column, this entire table will collapse. Because look, I have an ID called 1. I have 1 again. Somebody else has child number 1. Someone else has number 1. The whole table just goes away. That is what makes it weak. So that column absolutely has to remain forever. That is what weak means. Structurally, the table just collapses. Cool. So this might be an interview question. What makes something weak? then you should say, well, the PK, the PK that you borrowed from the other table needs to be there. Because if you remove it, the rest of the table would get duplicates. That's another way of saying in a composite primary key, every column matters. If you remove one of the columns, the rest of the columns might not be unique anymore. A weak entity also has a PK. Yeah, so in the weak entity, the PK is exactly that composite that we had. Okay, so once again, if this was the employee table, there was an employee ID, and then this is the children spouse table. Then if I make it so that there's now a composite with the employee ID, the column shows up again, and then some kind of a simple number, I'll just call it N. So if an employee 5 can have 5-1, 5-2, 5-3, that's what we're talking about. That makes this weak because it is existence dependent, and also this primary key is got tangled. Therefore, a weak entity, which is what this is, has a PK. I mean, every table will have a PK. So maybe what you're asking is maybe it has a compound PK. It will always have a compound PK, a part of which is coming from primary key of the other table. That's true for strong relation, right? If the PK is removed, the table collapses. Yeah, exactly. So even if this is, so what he's asking is a very good question. Suppose there's no existence dependent. It's an entirely separate table, entirely separate table. The fact that I make this primary key go here still is exactly what he's saying. If I go and delete this, then there's going to be duplicates. And that is standard composite key stuff, okay? But what he's saying is right. I'm very glad for all these questions, because it, in a way says that maybe you never thought about this in the past a lot, but now you have a chance to fully understand. These are not hard concepts at all. They're there for a logical reason, and they're amazing concepts. That's how the whole world of data, does not collapse on us, because somebody is guaranteeing all this. Having a weak relation, exactly, good. If you have a weak relation, I can call it a strong entity. Usually we don't use that word. All we say is if it is not weak, then it's a weak entity. Just leave it like that. If the relationship is strong, it's a weak entity. Only views don't have a PK. Don't even talk about views yet, okay? View is a derived table. You're jumping too far. Okay, so one last example of a weak entity. Suppose you have a loan, a bank gives out lots of loans to people. And so every loan has a loan ID. Obviously, the bank knows how much money you owe. It's a primary key for each loan. So there are 1 million customers in the bank. They give out all kinds of loans. To Trump, they gave out Deutsche Bank. Hundreds of millions of dollars of loans. Okay, then they go and make a payment, a loan payment. Okay, so that's a payment connected between the payment. So payment is also a table. So every time you make a payment, then every payment has a payment ID. The question is, what should the payment ID be? One answer, every time somebody deposits a check or wires money, all the payment IDs can be 1, 2, 3, 4, 5. The bank knows how many total payments there are, complete unique IDs. And this loan can be a foreign key somewhere. On the other hand, the payment ID can be a 2-column deal where every loan person, suppose I have a loan number of 5. I make one payment, I can be 5-1. I make a second payment, 5-2. I make a 50th payment, 5. The primary key gets tangled up. So 2 very different ways to do it, right? And that is what makes the difference between what and what. Again, here's the loan. It's a loan ID. Loan ID. Here's the payment information. So payment ID. There are 2 ways to do it. One of them is I can make the loan ID be over here. And then I can make a payment ID, which just simply is 1, 2, 3, 4, 5, increasing monotonic. Versus I can make it a very different way in which I can make the same payment table. Now my ID primary key is 2 columns. One column is the same loan ID and then payment number. So I can have 5-1, 5-2. I can have 6-4, 6-9. So which one is a weak entity? In which case does it make it a weak entity? Payment will become a weak entity when case A or case B. When does, which of these cases makes payment a weak entity? So weak entity means 2 things. You cannot have a payment without a loan. And also the primary keys are tangled, right? Yeah, B, okay? So you got crowd voted out, okay? So the wisdom of the crowd says to Surik, hey, think again. See, you agree, right? B is the answer because of the fact that that primary key is also repeated. It means if this column goes away, then 1 can occur many, many, many times. Everybody makes the first payment, then the number 1 would occur, and this table is not unique anymore. All those rows would collapse. That 1 would be collapsed to this 1. You don't know who made what payment, basically. The bank just goes crazy, right? Then they cannot credit you properly. So B is the answer. Yes. You guys understand. I love it. Understanding is some new connections between your neurons, by the way. That's what understanding is. Try and teach machine learning all this. I challenge you, there's no way in hell that you can take a bunch of data and teach a machine learning system what weak entity means. I challenge you. No. You can make rules for it. I'll challenge that too. Hey, look. What the hell, why not? I'll just go crazy. All right. So Polanyi was an amazing mathematician, right? So Polanyi had a philosophical concept called Polanyi's revenge. You should read that, okay? It's a brand new article. What? Okay, what the hell is that? It's a brand new thing. I think it was published today as a matter of fact. Okay, so this guy used to be the head of AAAI, the American Association for Artificial Intelligence. He talks about a very, very important idea called tacit knowledge. AI falls on its face and bloodies its nose because no AI system in the world today has tacit knowledge. So the machine learning engineers, that get all the Turing Awards, hate this idea and actually question the idea. They call tacit knowledge fake, but I'll tell you, tacit knowledge is not fake. Tacit knowledge is something that you and I have the moment we're born. So just calling it fake doesn't make it go away. So what he's trying to say, this guy is slamming Geoff Hinton. Geoff Hinton got the Nobel Prize for CS with 2 other people. Hinton loves deep learning. He thinks the entire world, like your brain and my brain, is going to be deep learning. Geoff Hinton is wrong. I'm sorry. Totally wrong. He keeps dreaming that you add more data to your machine learning and then it'll become intelligent. Snowball's chance in hell. That is what this guy says in more words. You can go read it. So what he's saying is, because of tacit knowledge, AI has no chance at all, which I actually happen to believe. So someday I'll tell you how to break what is revenge against Polanyi's revenge. Thankfully, it exists. Thank God. Otherwise, we'd give up on AI forever. We don't have to give up. Okay. So there's a weak entity, you understand. So how do you then represent a weak entity? Suppose an entity is weak because of the primary key business, and we understand, right? Just in Chen's notation, add 1 next to a rectangle. Makes it weak. Okay. So in Crowfoot notation, you really cannot tell. Go read the documentation. Each notation is, plus and minuses. But maybe you can tell by looking at it, okay? If all else fails, right, just look at it. Then you would know. But you should also logically know what this table is about, some extra information. Then that combination of the fact that a row here can only be, regardless of this here because of, an employee working at USC. And then you say, hey, look, this is also here. And then you can say, wow, now it's a weak entity. Okay, moving on. In reality, this is how it turns out in actual tables. Again, say this is USC, then somebody, Herman Washington, has an employee ID of 1003. Supposing you do it tangled, suppose you make dependent weak entity, this is what it looks like. That same employee, has multiple children, right? Annalise, Jorge. And so then the children are just numbered 1, 2. But thankfully, the ID is there to save the day. The combination makes it unique. Then this next employee, in fact, this person, 1003 only has 1 dependent, Suzanne. You see, right? 1, 2, 3 repeat. But this is also there. This also repeats, but the combination doesn't repeat. It makes this a weak entity. On the other hand, to make it a strong entity, what should I do? Well, or maybe a not weak entity. What should I do? What should we change here to make this not be weak anymore? We should change. Someone can type, talk. 9 new messages. Really? Oh, wow, wait. Why couldn't we make a table, 1 table for 1 customer? Well, you can, but it's all just an ease of searching through a mass bunch of data. Yeah, you can do that. And then you can take just the customer's ID and put it on some other table. Then you have a 2-level lookup. Isn't this crazy a number of tables? Yeah, exactly. So that might be the reason why you might not. Like Amazon might literally have 100 million different tables. But, maybe they're doing it. So B is weak entity, link to the article. Yeah, I will definitely put up a link to the article. This is great. I'll actually put it up on our extras for you to read. Seriously, you guys, this is goddamn important, okay? You can just bury your head in the sand and pretend that AI is intelligent. In a million years, what we have today will never get intelligent. I don't care if you have trillions of gigabytes of data, it will not be, I can guarantee you. On the other hand, if you take all this seriously and do something radically different, you actually have a chance of making a real AI that will talk to you like you and me someday. Add a primary, yeah, exactly, add a blank ID. So Zhang had the right answer. How do you make it not be weak anymore? Don't do it like this. Monotonically increment 1, 2, 3, 4, 5, 6, and make the employee number be some kind of foreign key. That's the answer. Okay, good. So you guys get it. Moving on, I want to tell you. This is pretty simple. This notion of, again, what's about minimums and maximums? What if the minimum for, a cardinality is 0? Like, what if a professor has 0 for the number of, courses they're teaching? Then the participation between the professor and number of courses taught is called optional participation, because the professor optionally can show up on the classes taught table. On the other hand, if the USC system says, if you're a professor at USC, you get paid. You need to minimum teach every course, some course somewhere. You must appear in the course catalog. Then it's called a mandatory participation. That means if I see a professor's name in the professor's table, and if I go look in all the courses that are being taught, like you guys want to apply for a grader, right? Then somewhere you're going to find my name. That is what a mandatory participation means. That's all it is. So again, this means a row. Okay, it's very simple. So one row does not require a corresponding foreign key entry somewhere else. It's all about the simple things that I told you. Wow, that's a cool question. This thing about bridge tables. I'll finish what I was saying, then I'll tell you that. Suppose these are all the professors at USC currently. So this is me with an ID of 100. These are all the courses that are currently being taught at USC. Every course is a course ID, all that. And then this is the professor ID, the employee ID. Mandatory participation means this 100 must appear here at least one time, and then up to a max of max times. Optional participation will happen when we say, this 100 does not have to be there at all. They're optionally participating because the minimum cardinality became 0, so we don't force them to have that relationship. That is all was being said in that little slide there. So easy to read. Optional means, again, this means row. So one row on the left-hand side does not require a corresponding, call entry somewhere in some other row. That's all. On the other hand, this opposite called mandatory means compulsory. Somewhere, somebody on the left-hand side must appear at least one time on the right-hand side. Does a bridge table make way in it? You think about it. So a bridge is coming from 2 different tables in which the bridge columns are primary keys. So then, given the bridge and one of those tables, is the bridge a weak entity or not? So again, here are all the students. Here are all the courses. Here is all the enrollment table. As a minimum, it has 2 columns. One is coming from student ID, the other one is coming from here. And so then the question just is between students and enrollment. First of all, is enrollment a dependent table or not? That's the question. What do you think? So would an entry be in the enrollment table without a student or a course? No, right? So enrollment is highly dependent, not on just one table, 2 tables. So it's doubly existence dependent. So clearly, existence dependent. Second is it could possibly be weak or not. If you delete some primary key, the whole thing will collapse, yes or no. Here, if you delete the primary key, absolutely it'll collapse. So it is also a strong relationship, doubly strong relationship. So it's a very interesting example. It's doubly existence dependent and also doubly strong. So it's doubly weak. Yeah, super weak. I like that. Weak squared. No, 2 weak. 2-star weak. So it is absolutely a weak entity. It's a really good question. Okay, think about it. All right. So CrossFit, once again, the circle line is just simply zeros and ones. So again, if USC says I need to teach between 0 and 3 courses, and I say, wow, vacation, I'm not going to teach this term, then you would see that symbol. On the other hand, if USC says teach at least 1 course, please, then you would see 1 many. Again, minimum 1, maximum 1, you would see parallel lines. Minimum 0, maximum 1, you would see like that. Yeah, cool. Any questions on this? So 0 or 1, so one side is optional. Again, because it is optional, that value can be a 0. It's not forced to be 0 or 1. Again, this can occur, for example, in a store that can have no manager. Maybe the employees just run it themselves. So therefore, going from employee to store, if an employee is a manager, they're going to show up in some store, but not the other way around. Some store can be without a manager. Then you would see something like that. Okay, so think of real world examples of where you would apply these diagrams. 708. All right, so again, course means CS 585, class means sections. This is very interesting. A course generates these multiple sections, but what do you think 1, 1, 0, n means? Well, let me read this first of all. If a table is dependent but has a weak relationship, that is a strong entity. If a table is dependent, yeah, you could call it that, okay? Yeah, one of the questions was if a table is dependent, meaning existence dependent, but then the primary keys are not tied together. What do you call it? A strong entity. You know, we don't say the word strong entity, okay? Strong entity really means not even existence dependent. In dependency, we don't use the word strong. Does Chen model share the same notation as Griffith? It seems like it, but yes and no. The Chen has more flyouts and more like parallel lines and so forth. This looks more like class diagrams. So the answer is no. Crossfoot, exactly. Those symbols are not shared in Chen. Most of the time, when we say min one, there can be exceptions. Yeah, leave of absence, all that is handled entirely separately. One min means when I go in the course catalog, I would see any USC paid professor, the name at least one time. These are extra things that are not part of table design, okay? Okay, let me ask you my question then. What does it mean for a course to have a 0 here and here? Suppose a course was Introduction to Computational Geometry. We have a cool course in the CS department called Introduction to Computational Geometry. It is so cool that you hardly ever see it in the course catalog because an amazing professor that teaches it, Aristide Rakisha, he just decides to teach every few years when he feels like it. And it's an amazing course. If you ever see his name, take it. But most of the time it is not offered exactly. So therefore, we maintain that course number in the course catalog so we never lose it. Yeah, unavailable, exactly. All these are the same answer. Good. That's what the 0 means. On the other hand, 1 means any legal CS course must be offered, at least one section. On the other hand, if a section is offered, it comes exactly from one and only course. Okay, that is why backwards it is min 1, max 1. 1, 1 means one and only. Hey, cool. Okay. So this is opposite of what we had before. I'm not going to go back. Okay. If you ever see this, it means every course that again is in the the syllabus somewhere must be offered every term. That's what that last one meant. Otherwise, nothing is different. It literally changed from 1 to 0. Okay, so this is all like extra fun we can have. This is all about tables. How many tables can be connected at one time? Every example that we ever saw looks like 2 tables are connected, right? That is called a binary relationship. These are all binaries. All these are basically everything is a binary. But it turns out you can connect a table to itself. What does that mean? The hell? That's like in fact, you can do it multiple times. That is called a unary relationship. Wow, that is weird. Okay. 1 table, not even 2 tables. Connect a table to itself. All that means is some primary key value can show up in the same table. Suppose there's a foreign key, but then these columns are the same, but they're named differently. Say you call this employee ID, okay? Say you call this like manager ID or there's something different. Obviously, column names cannot repeat, but the values are meant to be the same value, meaning suppose this says 6, this also says 6, then we understand that this 6 is that person. In that sense, you can connect a table to itself. Suppose the 6 was also here. Suppose the 6 was also here. The 6 occurs many times. So there's a one-to-many relationship between this table and itself. Wow. Because a manager can manage multiple employees. So this employee 4, this employee 2, and this employee number 0, the first employee in the company, they all have this manager called 6, and that's exactly what it means. And 6 themselves might have a manager called 7, except 7 is Jeff Bezos. This is, I have no managers, bitches. Sorry. So then that's the only person in the entire table that is allowed to be null, okay? Everybody else has a manager. So Jeff sits here with this $200 billion, says, nobody above me. God is above me, damn it. So then he or she oversees a few product managers, and they're all thousands of them. So everyone's going to have a manager except the root node. And that is the only one that's allowed to be null. Otherwise, everyone can have a manager. That's a table related to itself. Incredible, right? This is recursive. Yeah, that's right. Well, yeah, I'm not going to go there. Yeah. Hey, they got there in 2 different ways, Tesla stock is inflated. Deal with it. Elon Musk says we should all get up and move to Mars. Science fiction, you guys. Don't. It's easier to dig a hole under the ocean and go there, okay, than go to Mars. Mars is not just some Disneyland, okay? Yeah, just don't even go there. You can even go to the moon, all right? Knock it off. All right. So no playing games. This is recursive because once someone is a manager, that manager also can have a manager. That person can have a manager, and so on. That is why there can be multiple. I told you, right? If 6 has a manager called 7, 7 can have a manager called 100, and 100 can have a manager called 20. This stops only when you get to the top person. Therefore, you can have a recursive unary relationship. Sometimes it is not recursive. Sometimes it is only one. I might as well ask you, we are discussion is coming up. In terms of courses and stuff, what unary relationship can you think of? Just courses. Every course in the CS department listed right here. Every course. Each course is listed. Beautiful, beautiful. Prerequisites. Fantastic. I can have a prerequisite. CS 104, CS 104 would have 103 as the prerequisite. 210 might have 104 as the prerequisite. So this can also be recursive, okay? Good. Very good. There might be something else that's unary relationship that is not recursive. What example can you give me? I'm smiling because it's a funny example. It involves humans. And if I tell you what it is and you make it recursive, then you will also smile because it's funny. Okay, again, employees. A college environment is like a big, it's like a big fish pond where you have basically unlimited number of partners. You can meet and date and choose to get married or not. When you go work at Facebook and LinkedIn, look around and you say, oh my God, my cubicle has 4 people whom I see year after year. My chances of getting married and dating just went down to hell. So you date the person next to you, right? Hey, want to go out for coffee? So what happens is another employee get married, hopefully to each other. Okay, this is why it cannot be recursive. I'm married to you, you're married to somebody else. I don't even want to know. Okay, no cluster stuff allowed. Okay, so then hopefully it's like a mutually, pointing like deal going on, and otherwise it is not recursive. Okay, that's really all. So a spouse relationship, hopefully it's 2 ways, like I said, but then they're like married to each other. Cool. So therefore, this recursion doesn't need to keep happening. So unary does not always mean recursive, but it could be recursive or not. Okay, so I've told you all of this. Binary is the most common example. We've seen many of these. What about ternary? There might be 3 things in the world that might be linked together. I'll tell you a secret, okay? If you look carefully enough, you can even take 5 entities if you want, and actually amazingly link them together. So there's nothing magical about unary or binary or ternary that we have not talked about yet, or pentenary, 5, or quaternary. There are more common examples in the world than you would imagine. It is not that these are so uncommon. All you have to do is look. So let's talk about ternary. What if there was a table here, a table here, and a table here? Some kind of a 3-way partnership going on between all those tables. That is called a ternary relationship. To make it practical, you can think of some kind of a new entity that makes the relationship be real. And in that relationship, what we're saying is, I'll tell you, something from here and something from here and something from here. We only talk about primary keys from now on. Others don't really matter. Would become one row. Would become like one row. So you're tying like 3 different things together from 3 different tables and making like one row out of it. And that is going to be unique, meaning somebody else and the same thing would be a new row, and that's totally okay because that somebody else makes that whole triple combination unique. What is a pretty common situation that you can think of? I'll start dropping hints, okay? Can you explain recursive? Recursive means a row is pointing to a different row. That's why it's recursive in the same table. So this row is pointing to this row because this person's manager is that person. But then this row, this person also has a new manager, and that person also has a manager, and that manager also has a manager, and that manager has a manager. So when you jump from row to row to row, that is recursive. Can recursive call? Yeah, absolutely. If you go in a table and like screw things up, then they're literally going in a cycle. But in the real world, that doesn't exist, right? A CEO all of a sudden, cannot report to the person in the mail room, okay? Then you don't have a hierarchy. You don't have an org chart. You're more like a flat or some kind of network relationship. Some companies exist like that, by the way. There's no CEO. So it's not an error per se, but then classically you don't allow that. Yeah. So the short answer is yes. Circular report. Exactly. Circular reporting. You have somebody to blame always, so you say, who should I blame? I'll blame my manager. Okay, well, what goes around comes around. Okay, the buck doesn't stop anywhere. So we shouldn't really have all that. Cool. So funny. Okay, going back to my question. What is this? Start dropping hints. COVID-19. Oh, that's a big hint. One of my students in a different course, not 585, sent a letter which actually says she's COVID-19. Exactly. Very nice. Very nice. What about the doctor? One of them is the doctor. Three, that is really not a relationship. I mean, that's a very interesting example, right? I have to actually think about what he even said, but that is not what this is really about, okay? Hold on to that thought. I mean, that blows my mind. I don't think that is right, but it sounds cool. A doctor, meaning every doctor in Los Angeles. Yes, see, you're starting to get it. Between all of you, crowdsourcing collectively the answer emerges. Every single doctor in LA has a state-issued doctor ID. Every patient in the LA hospital system has a patient ID. CVS knows what your patient ID is. Every drug, every legal drug, to go buy in a pharmacy has a drug RX number. These are serious, by the way. Right. So then something ties doctor, patient. This is amazingly cool. For now, I'll go at drugs, okay? Then what is the sheet of paper? Good. Prescription. Fantastic. So prescription, ultimately, no matter how it's formatted, is a 3-column primary key business where doctor ID, patient ID, drug ID appears. Beautiful. Student exam answer record. Sure, why not? There are so many ternary relationships in the world. All you need is 3 columns that together make sense, okay? Hotel room booking. Good. Wow. I think our discussion can be short. These are things that I ask you, actually. If we're going the discussion, I ask you more questions about them, okay? But you're already answering them. Okay? Yeah. So, what? Oh my God. No way. Well, I'll tell you what. We can fix it. It's easy. No, it went to week 3. I clicked on the wrong one. Never mind. Usually very careful. That's much better. Don't fail, please. Just W2, okay? If all else fails, just type W2. It'll come up. It's week 2 after all. Impatient? It's not weird law, right? Elevator button. The more I click, the faster it loads. Don't do that. Eleve acceleration. See, look at this. Another example of ternary relationship. Yeah, so all these things are named are fantastic. Okay, there's even more. In the exam, I might ask stuff like that. So please come up with new ones. Yeah, technically, maybe not booking. I might go and criticize that. Yes. I could change that to something else, okay? Use of Sonar or something. Technically not booking, you're right. In fact, a booking might be an information between a customer ID and a room number. Yes, it's a bridge actually. True. So, Okay, so I want to this thing here. We still have stuff to go. Okay, ternary is obvious. Likewise, quaternary. Quaternary just simply means in a table, a bridge table, there are 4 columns and all columns are important. You can always find a relationship between 4 things. Even a professor-student course, please think about all that, okay? There are all kinds of things. Food. So look in the food category, calories, ingredients, food groups, supermarkets, think. So I can give you any domain. I can give you airport. I can give you hospital. I can give you supermarket. I can give you restaurant, university. You will find me a ternary or a binary, quaternary, unary relationship. They all exist everywhere. You just have to look for them. Okay. So look at this. Unary manages. So we did that. Binary, quite obvious, teaches, etc. Ternary, conceptual in the sense I don't have a table for it. I'm just saying logically I can link all of them. But in reality, what does the link actually mean? Then we call it logical. So conceptual means you just simply don't draw that entity. Logical means you end up actually making an entity. And the entity is going to be prescription. Yes, so binary. No, I mean, not really. There's no bridge here. It's not true. Binary just means, like 1 to 1, 1 to many, many to many, between 2 tables, like a painter painting. That's all binary is. A bridge is if these are students and these are courses, and then it's many to many, and they make a new bridge, that enrollment would then be, I see. Binary logical. Yeah, so if I go back to students, yeah, you're right. So sorry, I didn't catch what you said. It's a very smart thing that you said. Sorry. If these are students, These are courses. Yeah, and if I tell you, it's a binary relationship, yes, it becomes a bridge. Sorry about that. What's was pretty smart. In reality, all those, those dots would turn into bridges. Okay, that's actually all it is. Yeah, good. So this can be 2, this can be 3. If there's a 3-way partnership going on, student courses and even rooms or something, I can make that a ternary and actually put the room number there. So we really can make, even that simple example of students and courses. Yeah, the student is taking the course, but what room number? And I can make that a 3-way bridge. Then it becomes a ternary relationship. Yeah, why not? Okay. So we explained this again, conceptual versus logical. Logical is when you actually have to define, like name the table. Okay. So ER diagram, relationship. How do you then, in the notation, do it? Again, married. An employee can be married to, 0 other employee, right? Married. And likewise, hopefully only one employee max, right? So 0 to 1. There's no polygamy, polyandry, all that's not going on. Okay. So will the prescription table have the composite primary? Absolutely. Absolutely. Yes, those 3 are the primary. And you can have something else, maybe how many times, that particular doctor for that particular patient filled that particular drug. The county wants to track that because you don't want to go by your OxyContin 10 times a day, right? They'll put a limit on that and come and arrest you. So they'll arrest the doctor. So yes, in reality, you can have extra columns, but those 3 are the magic. I love your questions. Good. All right, so this married to is clearly a 0 to 1 thing going on. A manager manages multiple employees. An employee is managed only by one manager. Once again, a manager is like a head, it's the brain, for your body. You should not have more than one head. So many employees, that's why the org charts all go like a tree, because a manager, like a node, has multiple children, and then they can have multiple children. It hardly is inverted, it's weird. A course is many to many, and again, prerequisites, right? This should say has prerequisite, then it's a many to many. Because a course can serve as a prerequisite for many courses, and a higher level course like machine learning can have a chain of prerequisites, so it goes both ways. All right. More. Okay, so we talked about the bridge a lot of times. Bridge has another name as well. We call them associative because it associates 2 different or 3 different, 4 different primary keys together. So bridge is also called associative entity. Sometimes it's called a composite entity. Again, not a composite key, a very different thing. Composite entity because it's a whole table. It's a composite of multiple primary keys. Understand? And then most commonly it is done for M to N, right? Because again, I told you in a student table, I cannot repeat the student row many times and put 5 times that same information because they take 5 courses. I shouldn't pollute the student. I shouldn't pollute CS585 entry by having 390 names there. It's weird. So you need to make a new table that is less polluting. It is all about redundancy. It is minimizing the information that is stored. So you only want to store as little information as possible that still establishes the connection between students and courses. So make a new table and then leave the rest of the information alone and then archive this table. The rest still survives. All right. So in one term, relationship with parent entity is composed of the primary keys for each parent entity. Yes, so we talked about all, I'll get to all this, another time. But basically this talks about, different kinds of bridges that we can have. So this will come back to when I talk about extended diagrams, but this is easy. We've talked about this many times. I can have again students and courses, but I can have a GPA column or something that is not really required. But if you have a table, why not just make some extra columns that are not prime columns and just put some extra information there. Okay. Yeah, so then how do you, this is something you can do, right? This is what the whole enrollment is all about. Again, M to N, conceptually, you don't want to put like too many information in either side table. So you make a new table. Imagine only students, 2 students somewhere. Imagine only 3 courses ever being offered. But that student 452 is taking this class and also this class and this class. That student is actually taking all 3 courses. So their number appears 3 times. But it's not bad because the combination course number makes that combination unique. In other words, this comma this, supposing every student took every course, you'll have a maximum of 6 rows. That's basically what appears to happen here. And anything less than that. At USC, we don't do that, right? There's 40,000 of you, and maybe 3,000 courses being offered. Not every student takes the 3,000 courses. So it'll be less than M times N. But any combination is unique. And then here's the extra column. This column serves no useful purpose, but might as well do it. because it's a good place to store it. All right, so in the ER diagram, how do you, show the composite? You'll actually make a new table, and then you can simply have one-to-many going both directions, because it's really what it is, right? It is one class can have many students, and a student can be in many classes. But in reality, legally speaking, you're not allowed to do the diagram going both ways, right? Because again, you cannot, have all those extra columns. So then we pretend that, you make a new, not pretend, you actually do it for you. You make a new table and make a one-to-many, one-to-many. That means a student ID can occur here many times, just like I showed you before. The student ID can occur, so many times, right? 14, 14, 18, 18, 21. Likewise, a course ID can also occur many times. Class code. Sorry, I said the opposite. So student 452 occurs many times. 457 also occurs many times. Likewise, the course number also occurs many times. So here you can repeat as much as you want, but you're not wasting space. You're only wasting as little space as necessary. If you don't even do this, then nobody knows who registered what. But you don't have superficial columns. You leave it all up to here. These are like pointers in a way, okay? They're like addresses of the whole row. They store just simply pointer information, because that can point to everything else about the course. Just think of them as pointers. These all have direct analogs in programming for the same reason. Don't repeat code. Don't repeat blocks of memory, just point to it. All right, so we're going to finish with some fun. How do you put the ER diagram together? So now you know all the pieces, right? You ask, what kind of entities do I need? What kind of relationships do they have? Are there recursive relationships? What are the cardinalities? What are the connectivities? What are primary keys? What are required keys? What is optional? What is mandatory? So you know all the pieces. You ask all these questions. Come up with all of these, and then finally make a cool diagram and make a presentation and go, wow, great database. Go make it. So what do? You make the DR diagram using everything that I showed you so far. It's a detailed narrative of the operations. So this is one-stop shop. I know exactly how your outfit works. I just have to look at your database. Identifies business rules based on description. This is before you come up with the ER diagram. So get all the rules, and then from the rules, get those tables and wires, and then make an initial pass version 0.1. And in there, mark all the columns, and then mark all the primary keys. And then go make a presentation to management and say, what about trophies that USC won? You have sports, but you have no place to store the trophies. Okay, I'll make a trophy table and point sports to it. So you need to make revisions just like class diagrams. You don't make a class hierarchy in one pass. You have to keep revising, but that's good. It means people are interested. They're giving you feedback. So do it, and afterwards, you have the whole diagram. How do you make the diagram from little pieces? So this is one piece that only talks about enrollment. A professor. This one is dean, by the way. So every school like Viterbi, they pick from all the professors one professor, Yanis Yordas, and says Yanis is the professor Yordas is the dean of that school. So, but not everybody is a dean. Therefore, a professor can be 0 times as dean. So make the dean connection. And then a school such as Viterbi operates so many departments: civil engineering, computer science, aeronautical engineering, material science. And so that way a school operates at least one department. Otherwise, the school has no reason to exist. Keck School of Medicine has so many departments, cancer oncology, for example. All right. And then this is about departments offering so many courses. And once again, courses just simply, mean like actually CS 585. So it offers all of those. And then you see like all the extra columns, right? And that's one piece. Another piece is a course now generates sections. So class is a section. So CS 585 has 2 sections. It has a den section and also a so-called on-campus OC. So it says OC versus den. You go look there. So you understand that. We also understand about employment. Again, a professor with a unique ID can be employed by the department. A department employs multiple professors, and a professor usually is employed only by one department. I can have an associate professor, title in chemical engineering, but they don't officially pay me, so I'm only listed in CS. Okay, so we have that. Chair is very interesting because, a department, has a chair. A department only has one chair. And then a professor, if they're a chair, they can even be a chair of 0 department, meaning I'm not a chair. So not everyone is a chair. That's what this is. So if you're a chair, you're only there one time, usually 0 times. So this all makes sense to you. Likewise, I teach between 0 and n classes. That's what this is, or maybe 1 and n. And then this is you guys. So a student can enroll in multiple classes or not. You can just take the reduced course load. It just basically, go away. Just take the term off. Likewise, a class, sometimes probably it's not offered. And so, then maybe nobody enrolls, but a lot of people enroll. These are just business rule dependent. We can easily make it one if you want. And then a department has so many students. So officially, you guys declare your majors, and then you are all now part of CS, for instance. Maybe there can be a department with no students at all, freshly formed. Or a student just came in and for 2 years did not declare their major, and so then they have no department. So it can go both ways, zero minimum cardinality. And then advising, so many professors advise students on the side, but you don't have to. So a professor can advise between 0 and multiple students. And a student, if they have an advisor, they have exactly one-on-one. Students are required to have advisors. You have somebody to talk to. They'll send you a student advisor or a professor in this case, maybe in this school. What if a school always offers a professor for you to talk? Then it is 1-1. Sometimes if they say it's up to student, if they don't want it, they don't have to have a professor, then that would become 0. If they have, it's 1, otherwise it is 0. Okay, so then this last one is buildings, physical buildings. Building code like SGM, room numbers like, 124, 123. So a building obviously has multiple rooms. And each room can be used for multiple classes throughout the day. That is what this is, okay? So once again, think of why all this is. Okay, so these are great, right? And then you can just list, rather than a diagram form, if you want it to be more compact, you just go in HTML, make a little table, and list all of those tables. They're all entities. These are all tables, like meaning rectangular data holders. Everyone would have rows and rows and rows of ID. And some of them repeat multiple times because you're trying to make a relationship. Meaning uniquely, there's only school, department, course, professor, student, building, room. But you repeat professor many times because of this, because of the relationship. A professor can participate in multiple binary relationships. There's a dean participation, where most of us really don't participate. As a dean of a school, only Yanis does in which way. Likewise, chair also, most of us don't participate. Teaching, a lot of us do participate. So you have these participations, that's what this is. And then the connectivity. Is it one-to-one, one-to-many, many-to-many? This all now so clear to you, right? A school can have many departments, obviously. A department has many students. A department has many professors, has many courses. The course generates many sections. Then you're only a dean of one school, if at all. Okay, so that's clear. Full schema. So now you put all of those together. If I put blinders on you and walk to you, across a room where on a giant wall all this is scribbled, I'm showing you one tiny piece at a time, right? A little tiny piece at a time. And somebody says, can you just merge all of them? Meaning this professor rectangle is the same as some other professor rectangle, just fuse them together so that it's all in one place. That is what this is. So we can have some fun, right? 7:37. We'll stop after this. Get ready. Some fun. Really. Okay.
Hey, look at John, will you? What's the matter, John, love?
What's the matter?
New and blue amenities have been sighted within the vicinity of this
Look
theatre.
at that.
Oh, there's only one way to go out. How's that? Singing.
Singing.
1, 2, 3, ah!
Sing.
1,
2, 3, 4. Can I have a little more? 5, 6, 7, 8, 9, 10. I love you.
A,
B, C, D. Can I bring my friend to tea? E, F,
G, H, I, J,
I love you. Boom, 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 boom. Sail the ship. Boom, boom. Chop the tree. Boom, boom, boom. Skip the rope. Boom, boom. Look at me. All together now. 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 Woo! And that is how we go out. All together now. So now you'll never forget. All together now. Yeah. Hey, streamed live. That's cool, right? So this means you can take like everything that was in the table. Yeah, we should. If someone is serious, we can just have so much fun. Take all this and make this lovely diagram and just annotate the heck out of it. Just say everything. And then someone would walk up to it and go, wow, this is beautiful. If something is missing, then it's time to add it, okay? So afterwards, you turn all this into like a real SQL. and then start putting data into it. So supposedly this is how CSA's databases were designed. All right, so we should take a break at 7:39, come back at about 7:50, and we will do some questions. But I also want to actually, maybe go a little bit more and at least talk about the relational model, still more of the same. So why don't we take literally a break between 7:40 and 7:50, okay? To see you at 7:50. All right, stop share. Okay, the fun continues now. I'm gonna put up my chat window. And, oh, no, you're on the bottom. How do you do that? Hide thumbnail. Okay, I want to see you guys. All right, so why is the cardinality max optional for crowsfoot 0 max enough? Is max not important if min is 0? I mean, max and min are two different things. I would say, they are. Okay, so in crowsfoot, you still see two symbols, right? You see a circle, and then you see a line. So the circle is 0, the line is 1. So we actually never leave them out. Meaning either numerically, we say things like 0, n, 0, 1, 1, 1, etc., or 1, n. Or in crowsfoot notation, you draw the circles. Is that what you're asking? You're not going to leave it out. So there's still a way to specify that. Let me actually go there. We can see those. We cannot see those. No, I didn't show it to anybody. Sorry. I'm just talking. You can see my browser, right? See my browser? Yeah, good. Okay. Now it's just chatting away like this. Let's actually do it from here. Yeah, right. So I just meant to say that you still would use this, right? You would still say this. So from both directions, and I'm just going to draw it just to show you. So 1 to many, so 0 to 1, and then 1 to 1, and 0 many, and then 1 many. So in that sense, the 0 and 1 are still accounted for. Only when you have a weight situation of 0 and 0, minimum, maximum, then there's absolutely nothing. So that's the only case, that is not covered, right? There's no 0, 0, min, max. So think about that. If you have more questions, definitely I'll give you better examples. But in short, in cross notation also, you do express both mins and maxes, whether they're 0 or 1. Meaning a min of 0 is expressed like a circle, a min of 1 is expressed with a line. That's why when you see parallel lines, which is actually quite common, that means 1 min, 1 max, it means you must have 1 and only 1. You cannot have 0. Like many, I don't know, farmers markets, might even tell you, if you want to participate regularly, then, you have to come to every single event. You can participate only one time per event, stuff like that. I got confused in slide number 24. Only this time I'll very quickly go to that slide. But in general, we can try and maybe do different things during our discussion session. But for now, we'll just go there. 24. Oh yeah, this one there. In here, what we say is, again, you read it from here, like the course information is here. The class information is here. So when we say course 1N and then the crowsfoot notation, it means a course must be offered as a minimum of 1 section. It must some student must be able to take it. Or if the course is in heavy demand, they can be offered multiple sections like CS 104 years earlier. Therefore, this N corresponds to that foot. This 1 corresponds to that 1. Oh, the next slide, okay. And then conversely 1 to 1. Next slide. This slide or no? Can you answer? Is your confusion here or the 21? Okay, 21. This one, optional, mandatory. Right, yeah. So optional basically means there's a 0 somewhere. That's really all it is. Okay, so in a participation, if there's no 0 at all, because 0 means that's when you skip. I like this, We're playing like basically, like some kind of a iteration. Newton-Raphson, I like that. Converge. It's okay, I'm just having fun with you. No big deal. This one. Which one? So the 4 things that I mentioned are all here, right? Regardless of what the word says, it is what I'm trying to tell you, which is this means 0 or N. Like, for example, professors teaching courses. Oh yeah, the comments are a little bit more confusing than they need to be. So please go with what I'm saying, okay? This means just something very simple. It means, say again, professor and applied to courses they teach. This means I don't have to teach any course. I teach up to a maximum of whatever cardinality. On the other hand, this means I must teach at least one course and then I'm going to have some other maximum. And this means exactly 1 to 1. So minimum 1, maximum 1. This means minimum 0, maximum 1. Yeah, so, if this is not clear, then don't read it. That's all, okay? Whatever makes sense to you. Okay. In the remaining time, I'm going to go backwards, meaning, well, we have time till 8:20. So I'll tell you some extra stuff, meaning I'll introduce what I'm going to tell you, and then we will do some relational modeling, right? I'll ask you for some questions, definitely. I'm about roughly an hour behind, which is not much in the whole, bigger scheme of things. So we'll catch up. Dotted lines will represent, yeah, right. So in a relationship, usually you never do dotted lines. Dotted line might actually mean like not mandatory. It might mean an optional relationship. So if you ever use dotted lines in a relationship, it means if the cardinality all there is not specified, that means the row on the left-hand side might not appear, like a row on the right-hand side. What tool should we be using for homework? Yeah, the notation, most definitely, please use Crow's notation. And then we'll give you multiple pieces of software you can download. Like there's one called ER, what is it called? ERD. Forget. Yeah, ERWIN. There's one called ERWIN. Yeah, Dia is a very nice one, lowercase Unix there. So you have this. You also have something called ERWIN. We'll give you like all the titles, okay? The short answer is use whatever you want. As long as it makes sense to you, just use whatever you want. See, Irwin ERD, but some are Macs and PCs only specific to that one. Irwin Data Modeler is very cool. Or just use pencil and paper, that's totally fine. All right. So back here, I want to show you something from Extras and then introduce the actual notion of relational modeling. We're slowly getting towards building things like Oracle databases, okay? But you're, I think, starting to understand conceptually practically everything that I've said to you so far. Okay, I want to go in the Extras page and start literally backwards. So in my little break, I took the desktop thing and transferred it over here. So you can download this and you have the presentation that I made. It's got like all the information, right? So I'll skip that. And then, so one of you wanted the Polanyi's revenge. It's like AI's gotcha. AI almost blindly just searches for like the next big thing. So I've seen it for 30 years. So unfortunately, now this is not mainstream, by the way, and it's much harder than people think. But this article says there's really nothing else left. Like deep learning is basically it's not going to work. Expert systems are not going to work. So Subba Rao says there's not too many things you're going to work. I'll even go further than what he says, believe it or not. Like I'm more radical than him. So I'll tell you some other time, okay? But this is a good starting point, but we need more than this. No wonder AI has not been solved. Okay, so that was the Polanyi's revenge, which I call PR. This is very cool. This is more to our point. Okay, this is the paper that started it all. Like we would not have a database class today if it were not for the fact that the scientist, Dr. Ed Card, who was at IBM Almaden, right here in Silicon Valley, San Jose, California. He's a mathematician, so he, worked for IBM and did like cool math research. He's done a few other things as well, by the way. He's more than just this is the biggest thing that he did. So he writes this, he publishes this paper. And it's an amazing paper, okay, completely, basically game-changing paper. That's what this is. A relational model right there. They did not call them databases at the time. We call them data banks, okay? So a bank is just a bank of data. You can read this at your own time. I won't read them. But these are all like fields or column names, okay? So these are all entities. You understand now as entities. And then what goes where, what doesn't matter. Entities, columns. But he starts to present what is called a relational algebra. So then what he's saying to you is, in fact, these are all the ternary relationships, we talked about right there. So everything that I said today is, in fact, in a way here. You can have a four-way bridge, All right, so, but that is not that's not all he does. He says, what if a table were to be a data structure? So suppose a complex number is a data structure, obviously it's a kind of number. Then data structures instantly have not just members where you put the data, you also have methods, like what can you do with the complex number object? I can find the complex conjugate. That means I can just put a negative sign in front of the imaginary value. I can find the inverse of a complex number. I can multiply a complex number by another complex number. Say A dot multi B, Those are called methods, right? That's exactly what he did. So he said, if a table is like a piece of data, what operations, what methods can I do on tables? He named exactly 8 of them. That's what this is. So those 8, they all have these symbols you can read, okay? This is just simply, I mean, there's just no other way to put it. It's a mind-blowingly amazing paper. I probably should say it out. Then he went to his bosses at IBM and said, IBM should stop making the hierarchical models and the network models, databases that they sold at the time with words like vSAM, VSAM, like all kinds of, databases IBM sold. But then he said, this is far superior compared to all of those because you don't need a hierarchy of data types. You don't need a network. This can model basically any bunch of data as long as each data is just a row, of object, and then they have like columns which are attributes. Then his bosses at IBM said, haha, nice joke, get back to work. They basically ignored his paper. So weird, right? So till about the 1980s, Larry Ellison, whose name you can look up, was like a computer salesman, okay, somewhere in Kansas. So someone somehow gave Larry Ellison, R.I.P. Larry King, he's a cool guy. So Larry Ellison, this guy, 12s. Okay, so he was, selling computer stuff somewhere in Kansas. Someone gave him this paper and said, Larry, you should read this. He's not really a computer scientist, but somehow read this paper. Something told him, this is like a gold mine. It's a multi-billion-dollar idea. So he went to his wife, his ex-wife now, and he said, we need to mortgage our house and then take the money out of it. And I want to start a company. What for? I want to, write this new piece of software and sell it to the world. And the wife at the time said, okay, go ahead and do that. I'll divorce you. Larry said, deal. Then that's actually what happened, so he got a divorce. And then he used the money to start Oracle Corporation. So Oracle is the world's first relational database company that put this idea to good use. They implemented all those 8 relations, okay, that Carl talked about. So IBM was number 2 in the world. So Oracle started to take off like a rocket. And then IBM said, whoa, what did we do? We just said no to Ed. Sorry, Ed. So they were the world's second. And then others followed after that. So it's a supremely cool piece of history. And they rule the world, right? See, right now, Oracle today, they have a cloud offering of NoSQL databases. They're not about to be left behind by the new revolution. So they have a mixture of relational and non-relational, and it's all on Oracle Cloud. Yeah. So DB2 is horrible. Okay, it's an IBM product. Unless you're on mainframe, you would never even think about it. So I think you're fine. But now they have Cloud Oracle. Okay, so I have much more to tell you in the future classes. That's what all this is for. So we should jump. Yeah. Okay, so then therefore that paper became crucial. Okay, you can read the paper. It's so readable. The other thing I want to show you then is, then if that was 1985, like I said it was, then what about now? Genealogy. Mom, where did I come from? Came from your parents. Where did my parents come from? Came from their parents. So you can treat it all like one big genealogy project. And then, oh my God. Okay. So, if I were you, I would just load it locally. Okay. Just find a way to load it, okay? All right. So then you will actually see how cool this is all, because you can start with Oracle someplace on your left-hand side. See that? Okay. Wow. This is ridiculous. This is how many relational databases are in the world, okay? So look at all this. This is all pre-relational, okay? Like System-R, IBM, okay, Multics, Honeywell. There were all these companies. They all went by the wayside because somewhere up here, right? This is funny, Cod River, okay? So these are all IBM database. Sorry, these are Microsoft databases such as Paradox, Access, and Borland Corporation got into it, FoxPro. A lot of people still use FoxPro. Look at this. So Informix, Ingress, okay? These are amazing, right? So Empress, Oracle. Wow, one of the very left thingies. This yellow line is the main line to follow. Holy crap. And then Sybase SQL Server. Okay, so right now it's free. You can download it. At one point in the mid-80s, Oracle, Informix, and Sybase, they're all in Redwood City, just less than a mile from each other. I've driven on the 101, in the Bay Area. You will see all 3 buildings, okay? Now of the 3, only Oracle stands. The history is just fascinating about all this. In the meanwhile, so many. And this is written at UC Berkeley, so I'll tell you a lot about Postgres. As a matter of fact, Ingress and Postgres written by the same person. He won the Turing Award for databases, okay? So Michael Stonebraker, look him up. And then you might use this for your spatial databases homework. And then here's IBM Informix, a little bit more modern product. So this just keeps going, okay? So you can run VoltDB like on Amazon Cloud, okay? So these are this is where we are today. All these are available in the world, okay? Wow. So Oracle is like just one continuous line, and just like a wavefront, it keeps expanding, right? There are even more other things, Redshift again from Amazon. There's all kinds of things you can trace back to, but it's all about tracing back genealogy. Wow, where the hell did stuff come from? Pretty much all relational stuff, came from Oracle, or it came from somebody that merged with the Oracle branch. It's all like GitHub branches, right? This is the main branch, and they're like forks. Okay, cool. It is fascinating. Yeah, good. Oh, nice. Parlor use. I did not know that. Wow. It's too bad Postgres got associated with that. Micah Stonebreaker is a very cool guy. He's like a humble database, scientist. Wildly cool. He and his grad students at Berkeley first wrote Ingress, and then, they didn't like it. Then they wrote, oops, then they wrote Postgres. Should stop scrolling. All right. There was a crazy cool musical instrument called the sarangi. Okay. I'm going to spend a few minutes introducing this, and then we got to ask you some questions, all right? Okay. So what I'm going to tell you is this relational model. I showed you something pretty cool, this paper. So what is ultimately in that paper? We'll not go through all these slides. Maybe we'll go through 5 slides. But here's a speed tour, though, okay? Then we can come back. Okay, I want to read that. Relational modeling. Ultimately, next week, this is what I'll show you. So relation is, again, something connected to something. On the one hand, 2 entities connected. Or, I told you, every cell, every row is connected to every column. That is what this relation is. Again, relation is every row has a relation with every column. And that's what this is. Okay, so moving on, though. Tables. So this is all about tables. So what makes a table? And many things I've already said to you so far. A table has rows and columns. But one column or a small combination of columns is super important. It is called the key. Okay, so talk a lot about keys next time, but you already know so much, so we're going to go a little faster. And a key determines everything else. You give me your student ID, I'll find out all your academic history. That concept of using just one little number to find out everything else about you is called a determination, because all the other numbers are like dependent variables. In a way, you can calculate them, you can look them up. The only thing that is independent is the primary key. So this notion of determination, I'll go through all this again. So determinant is the key again. The key would determine everybody else who are called dependents. Your student ID will determine GPA. Student ID determines major. Student ID determines advisor's name. Student ID determines graduation date, on and on and on. All right, so we'll revisit that. And that is all. So that idea of depending is called functional dependency. If this word went away, the world wouldn't change. It's the exact same. It just means everything is dependent on a key. It's just key decides, which is determines everybody else, because they're non-keys. So the key, the whole key, and nothing but the key, so help me God. So, if you know about the US, you're going to smile. Okay. Because that's what you do. You swear in the Bible, right? I swear to speak nothing but the truth, the whole truth, and nothing but the truth. So help me, God. Okay, so help me, God. Cool. Like a Venn diagram, right? You've got like a little circle. You got like a square. Tell the whole circle. Tell the whole truth. Not a part of the truth. Not something else. Just the circle. In other words, don't take anything out. Don't add any new crap. Whole circle, please. Okay, so composite key, you already know. This means the key is made up of more than one column, like last name, first name. And this all just simply means every single row is unique. As soon as a row is repeated, meaning the primary is repeated, you lose this magical, important property called integrity. It's like losing your character. Nobody would ever trust you anymore. The table's character is gone. The table is dead. It'll happen if you repeat primary keys. So this is a way of saying every table, a good table, will always have this its most important property. This just simply means when you have primary keys and foreign keys, then what if a foreign key does not have a primary key? Like what if I leave USC and then my kids still are on the dependent table and they go look for me, I'm not there. Then I break something called referential integrity. Foreign key pointer is broken. If the foreign key pointer correctly exists, that is called referential integrity existing. Okay, we'll come back to every single one of these. So then you have, how do you get to a primary key? There are so many other things you can choose from, and therefore they are called super keys, candidate keys. But in the end, you settle on one, and then you never change your mind. And then you have like foreign keys. Secondary key is like a fake key, okay? A simple version of a primary key. It's not as strong as a primary key, but it works. So then that is all explaining stuff here. And then relations. So it all comes down to this whole link business. So when you have like Amazon selling so many things, who are the vendors? The vendor table. There is your primary key, foreign key, contact. That's the relation. So I'll use that as an example to illustrate all of CARD's 8 operators. So this is all about nulls. This is the reason why NoSQL came, because this is a rule that we used to follow, but the whole world, the consumers said, we'll have nulls anywhere we want. Who the hell are you to ask me for my information? So tables started to become full of holes. Then we abandoned tables altogether. Okay, this is where the whole thing starts. Ed Card named all these, mathematical operations. So he called it algebra. It just means, computations you can do. And this is simply, forget this. This means if you had a variable like programming language, what would you store the variable into? That's called a rel var. It holds a table, okay? Okay, so I'll tell you about closure. These are all these operations. So I'll tell you much more, but for now though, it's like this. What operations can you actually do? These are the operations. Project, select first of all. Give me only a few rows. Give me only a few columns. Merge 2 tables together. Tell me what is common between 2 tables, like set operation, set union, set intersection. Subtract 1 table from a different table. Tell me what the difference is. So these are just examples for select, project, union, intersect. Difference, subtract table A from table B. What is in A but not in B? Set operation. Multiply table A by table B. These are very interesting set and numerical operations, but you are operating on a whole table full of data with another table full of data. Subtraction. How do you subtract tables? What does it even mean? We'll revisit all this. I'm rushing through it just to show you what's coming. Joins are powerful. Again, how do you, at runtime, go and merge information from multiple tables and do the most complicated queries in the world? Not physical joining, meaning we don't make new tables and save them. SQL does it when it's running. Even more amazing, the most amazing of all, how do you take a table A and divide by table E? What does it even mean, okay? But that is one of 8 CARD's operators. Amazingly, all the other 7 are actually SQL commands. You can run them. There's a join command, there's a select command, there's a difference command, there's a union command, there's an intersection command, there's a project command. But there's no divide command. But divide is a cool operation. And we use divide in the world, actually. So join illustrations and natural joins, many kinds of joins. Left join, right join. Divide. See, you can actually divide tables. So if you're curious, you can go read this ahead of time, but we'll come back to all this next Wednesday. And this is not about relational tables at all. We have mentioned this before, which is, what if you want to hold information about the columns themselves, or how many rows are in there, or when was the table formed? All the meta information, we call it metadata. It is everything that is not in the actual cells. No, it's not the actual data, it's everything else. Even what data type is your string, like meaning how many characters maximum for your string. Okay, so we should come back to all of this, all right? Therefore, I can ask you a few questions, just so I can make you talk. Yeah. So please tell me, unary, we've named a bunch, right? So maybe this one I think we've done. Wait. Maybe I cannot ask you. We're actually a little stuck unless I go through those. Okay, give me another example of a unary relationship. So tell me something where a table relates to itself. What do you think? I can think of one. I'll start giving you hints. There's probably many more, right? But one thing instantly comes to mind. It is not anything we named already. It is not employees and managers. It is not people like, getting married, dating. Maybe somewhere else. I can have a table full of something and a row. Interesting. So what about a TA? Can you be a little bit more clear? A TA? You mean of all the students? Oh, I see. So there's, say, all the students, and say there's a TA column. So some students are TAs for other students. That's interesting. Friends of friends, for sure, absolutely. So Facebook loves stuff like this.
I'm thinking about having a listing of a bundled package of merchandises, and the bundle points to each individual item in that same table.
Wow.
So like a huge SKU table where you have a bundle SKU that is linked to other individual items in the same SKU table.
Okay. So what would be an example of bundling? Like what data? Like what type of data are we bundling?
I'm thinking about, for example, TV shows. Like if you buy the entire season, then the entire season bundle is
Oh,
Basically,
interesting.
it relates to every episode in the season.
Oh, wow. That's actually very cool. Wow. See, in Amazon, sometimes they bundle things, right? They literally bundle. They say if you buy this graphics tablet for $10 extra, we'll give you 2 extra pieces of software. Yeah, those can all be in one table and relate to each other. That's a great example. Master slave architecture, totally. Because machines can be linked to other machines, right? And they can be linked to other machines. You can have a table of all the machines, and there's literally this cable routing table that knows what is connected to what. It's beautiful. Computer network. Yeah. So in short, what you're saying, true. Employee and student. If you have, oh yeah, I see. So if you have a student table and there's a column called employee, some students can be employees, but employees are actually students. Okay, I like it all. How? Wow. It's so cool that you actually came up with it because it's the one thing that I was thinking of. Wow. Okay, so the FDA has this ultimate drug database, every single thing that you can ever buy at CVS, right? There are complications, okay? So if you take this drug along with the drug, you might get a heart attack. So they have all these tables that say, if you're taking this drug, then don't take the drug, don't take the drug. So that's a great example. 5 minutes, okay, thank you. Disease and symptoms. I see. But symptoms are not diseases, though. I might actually argue with you on that one, okay? Unless we think that symptoms are diseases. Symptoms can look like a disease. Like say I have a rash, okay, then, oh, I got a rash. But it's not a disease. It's telling you something else. You have like toxin in your body. So maybe not quite that Vignesh, but maybe you have something cool. I don't understand. That keep thinking though, think of something more. Or playing like, just freestyle brainstorming. Family, yeah, absolutely. This is a great one. If you list everyone in your family, right, you're all somehow related to each other. Great. Again, some kind of tree or a graph. Anytime you have a tree or a graph data structure, that's going to be an example. In biology, Linus's classification, right? So Linus, classification. That system is one massive self-unary relationship because you can put every single form of life in a table, and then you can know like where somebody came from. Like humans came from like apes, for example, and then they came from somewhere else. What? So trace it all the way back to like unicell, creature. Satellite offices and headquarters. Interesting. So if you list all of the offices, all the different units in one place, then some of them might have like a headquarters. Sure. Good. Wow. Every answer that you guys gave, possibly even that one. Yes, so yeah, exactly. So in an ecology, this is so true, So, there's a predator that has like a prey, right? But somebody else is going to, use the predator as a prey. So there's an alpha, predator at the top, right? Yeah, wow. Fantastic. Oh, I like that. Yeah. So again, if you have all the sports teams, right, then teams are playing against each other that can be in the same table. So these are fantastic examples. I think this group is the one so far, when I've taught this, has come with the most diverse example, have come with the most diverse examples. Billing receipts for fun. Yeah. Practically almost anything, believe it or not, okay? Because a refund is also issued like a new bill, but it has negative amounts in it. So in that sense, they relate back to themselves. I have like all kinds of, this is great. I'm glad we're recording all this. Okay, so I think we've done enough of that. What about maybe one more ternary? Although we should skip this as well because you guys showed me so much. Can you answer this? This might be a little too much. I guess all I'm asking is, when you have a composite primary key, such as last name and first name, then only if you give me a last name and a first name, I should be able to look anything else up. And that is what a composite primary key means. And that is called a full functional dependence, because every piece of information I'm asking for, you should give me. If you say no, then I cannot look anything else up. But imagine I have a weird primary key that I made for no good reason. My primary key is last name, comma, first name, comma, GPA. Like a weird key called last name, first name, GPA. So in such a case, I need something called full functional dependence, meaning I don't need from a student all three pieces of information because GPA is actually fake, okay? It's an extra column. So such a situation is called not full functional dependence, okay? So in a not full functional dependence situation, I don't need a value for all the little individual primary keys. Why is that a bad thing to have a situation like that? In other words, why is full functional a good idea? Why is partial functional, which is I don't need all the values, I only need some of the values, So why does it smell bad to you? You have to look through an extra field. That's one way to answer it. That is another way to answer it. But think about the extra field itself. So time is the third way to answer it. These are all, you're getting warmer, but there's something more bothersome than all of this. There's something more fundamentally wrong rather than having to look through storage time. These are all true. But what is something even worse? Exactly. I love that, TMI. So what the hell is GPA even doing as a primary key? How can GPA how can GPA possibly be a primary key, right? So we should not even have GPA as part of a primary key. So always strive for full functional dependence. All right, so I'm actually out of time, so let's stop, okay? So after I finish the rest, I'll ask you for all of these. Okay, we're still not ready for homework 1, you guys, so probably I'll give it to you. Well, I'll think about it. Maybe this weekend, you can start. Yeah, less is more, I like it. All right, bye everybody.